The International Space Station is one of the most incredible things humanity has ever built. A giant house floating more than 400 kilometers above the Earth. It travels at an unbelievable speed of 28,000 kilometers per hour, completing a full orbit of the planet every 90 minutes. We see it as a peaceful laboratory, but here is the difficult part most people don't imagine. Building something of this size in space is almost impossible. On Earth, we use cranes and the ground holds us up. But in space, everything floats and there is no up or down. Each piece, weighing thousands of kilograms, had to be perfectly fitted together by astronauts on dangerous spacewalks, where a single lost screw could cause a disaster. How did engineers manage to plan a construction where you can't hammer a nail and everything needs to work non-stop for decades? Prepare to fall asleep while listening to this video and discovering the secrets of this engineering. Subscribe to the channel, leave your like, and comment what part of the world you are watching from. Get comfortable and relax. Let's begin. Imagine trying to build a house while floating in a pool with no sense of which way is up. That is the daily reality for astronauts assembling a space station. The moment you leave Earth's gravity behind, every instinct and tool you rely on becomes useless, starting with the very concept of direction. In microgravity, there is no true up or down, which might sound liberating but quickly turns into a logistical nightmare. Simple actions like setting down a wrench become fraught with risk because if you let go, it does not fall to the floor, it drifts away, potentially becoming a lost item or, worse, a hazardous projectile moving at a steady pace until it hits something or someone. This floating environment means that nothing stays put unless it is securely fastened, and every object, from the tiniest bolt to a massive module, behaves in unpredictable ways. The absence of weight does not mean the absence of mass. Those large structures retain all their inertia, so if you start one moving, stopping it requires an equal and opposite force, which can be dangerously difficult to manage in a confined space. Astronauts must constantly fight this physics, using handholds and foot restraints to anchor themselves, but even that is exhausting. Every time they push against a surface to move, they might drift in the opposite direction, thanks to Newton's third law of motion. This means that a simple task like tightening a bolt could send an astronaut spinning slowly away from their work site, wasting precious time and energy as they stabilize themselves. The conservation of angular momentum is not just a textbook concept here. It is a practical challenge that affects every movement. Planning each operation requires meticulous consideration of how forces will interact in a three-dimensional, frictionless environment. For instance, if two astronauts are working together and one exerts force, both might end up moving in different directions, complicating coordination. The mental load is immense because astronauts cannot rely on muscle memory or terrestrial habits. They must consciously think through each action to avoid unintended consequences. This constant need for repositioning and stabilization consumes significant energy and time, which are limited resources in space missions. A job that might take an hour on Earth could stretch into several hours in orbit, not because the task itself is harder, but because the environment adds layers of complexity. Tools must be specially designed with tethers and magnetic features to prevent them from floating away, and workstations need to be ergonomically arranged for floating users, which is a contradiction in terms. The lack of a stable work platform means that even reading a manual or consulting a diagram becomes a two-handed affair, one to hold the document and one to hold yourself in place. This fundamental obstacle of microgravity impacts not only construction, but also daily maintenance and repairs. For example, if a component needs to be replaced, the astronaut must first secure themselves, then secure the new part, and then manage the old one, all while ensuring that no loose items escape into the cabin. The psychological effect is also notable. Without the familiar reference of gravity, spatial disorientation can occur. making it hard to judge distances or orientations. This can lead to errors in assembly or even accidents if someone misjudges the trajectory of a moving object. In essence, building in space is like assembling an intricate puzzle while riding a roller coaster in the dark. You are never quite sure which way you are facing, and every piece has a mind of its own. The challenges extend to the materials and structures themselves. On Earth, gravity helps align and settle components, but in orbit, everything floats, so modules must be designed to connect perfectly without the aid of weight to pull them into place. This requires ultra-precise engineering and robotics to guide parts together, as even a millimetre of misalignment could prevent a secure seal. Astronauts train for years in underwater pools that simulate weightlessness, but those simulations cannot fully replicate the persistent floating of space, in the pool. There is still some drag and a sense of down due to buoyancy, whereas in orbit, the sensation is truly neutral. This training helps, but the real environment always presents surprises. Moreover, the absence of gravity means that fluids behave differently, which can affect cooling systems or hydraulic mechanisms used in construction equipment. Dust and debris do not settle, they float around, posing risks to equipment and health if inhaled. The cumulative effect of these microgravity challenges is that every aspect of construction must be rethought from the ground up, demanding innovations in technology, procedure, and human adaptation. It is not just about building something. It is about creating a habitable structure in a realm where the basic rules of physics we take for granted no longer apply. This foundational issue of microgravity and the lack of reference points is why space station construction is a monumental achievement of human ingenuity, requiring relentless problem solving and a deep understanding of orbital mechanics. As we continue to push the boundaries of space exploration, overcoming these hurdles will be crucial for future missions to the Moon, Mars, and beyond, where similar gravitational challenges will await. The lessons learned from building the International Space Station underscore that in space, even the simplest tasks are feats of engineering and human endurance. So next time you look up at the night sky and see a bright dot moving steadily, remember that it is a testament to our ability to adapt and build in the most unforgiving environment imaginable, building on that reality of floating construction. The next monumental hurdle was actually getting all the pieces up there and fitting them together with absolute perfection. Think about it. You cannot just launch a fully built space station in one go. The International Space Station was constructed piece by piece, like the most complex Lego set imaginable, with each module launched on a separate rocket over a period of more than 10 years. Each of these modules is roughly the size of a school bus, and they had to be engineered to withstand the brutal violence of a rocket launch, strapped to the top of a controlled explosion. These components experience immense vibrations, G-forces, and pressure changes that would tear a less robust structure apart. Once they survive that harrowing ride and reach the vacuum of space, the real delicate work begins. They have to be manoeuvred with incredible care to dock with the existing structure, and this is where millimetre precision becomes not just an ideal, but a life or death requirement. The docking mechanisms are masterpieces of engineering, involving a complex dance of latches, seals, and guides that must align perfectly. We are talking about tolerances smaller than the width of a coin. If two modules are off by even a centimetre, the consequences could be catastrophic. The electrical connectors, fluid lines for water and coolant, and air passageways all need to seal flawlessly on the first attempt. A misalignment could mean a module worth billions of dollars becomes a useless, floating hulk, unable to transfer power, data, dot, or life-sustaining air to the rest of the station. This is not like plugging in a USB cable where you can just flip it over. It is a one-shot deal happening in the unforgiving environment of orbit. The entire sequence of assembly was choreographed years in advance with meticulous detail. You could not just add modules in any random order. the station had to grow organically, with each new piece relying on the power, stability, and resources provided by the modules already in place. For instance, the early Russian Zarya module provided the initial propulsion and power, acting as a foundation that later modules like the Unity node attached to. This dependency created a critical path where any delay in one launch could ripple through the entire construction timeline, holding up subsequent missions and putting the entire project at risk. This was, in essence, an interplanetary supply chain of unprecedented complexity, coordinating the launch schedules of rockets from different countries. The American Space Shuttle, the Russian Proton and Soyuz rockets, was a logistical nightmare fraught with political, technical, and weather-related delays. Each launch window had to be calculated precisely, and the modules had to be stored and prepared on Earth, waiting for their turn to fly. Once a module was in orbit, the astronauts had to perform spacewalks and use robotic arms to carefully guide them into their final position. The Canadian-built Canadarm2, a massive robotic arm, became an essential tool for this process, acting as a giant, precise hand that could grapple incoming modules and gently berth them to the station. The astronauts controlling this arm underwent extensive training, as a single wrong move could cause a collision, damaging both the new module and the existing station. The assembly was not a continuous process. There were long gaps between module launches, sometimes years, during which the station had to remain operational and stable with its incomplete structure. This stop-and-start nature added another layer of difficulty, as systems had to be designed to function in both interim and final configurations. Furthermore, the modules were built by different international partners, each with their own engineering standards and protocols. Ensuring that an American-built module could seamlessly connect to a Russian-built module, and later to modules from Europe and Japan, required an immense amount of international collaboration and standardization. Every bolt, every connector, every software interface had to be agreed upon years in advance. This was not just about physical connections. It was about making sure the electrical grids were compatible, the computer systems could talk to each other, and the environmental systems could function as a unified whole. The margin for error was virtually zero. On Earth, if you are building a house and a window frame is a little off, you can shim it or reframe it. In space, there are no second chances. No quick runs to the hardware store for a replacement part. Every component had to be perfect before it left the ground. The engineers performed countless tests on Earth, building full-scale mock-ups and simulating the docking procedures in giant water tanks to practice in simulated weightlessness. Yet, despite all the preparation, the actual assembly in space was always a high-stakes operation. The astronauts involved described the intense focus required during these docking procedures, knowing that a mistake could not only ruin the mission but also jeopardize the lives of the crew and the future of the entire station. The logistics also extended to the crew themselves. Astronauts had to be launched to the station to perform the assembly work, which meant coordinating their travel on separate spacecraft, like the Soyuz or the Space Shuttle, and ensuring they arrived with the necessary tools and training for the specific tasks at hand. Their time was extremely valuable and limited, so every minute of their schedule was planned to maximize efficiency. They rehearsed the assembly steps over and over on the ground, so that in space, they could work almost by muscle memory, despite the disorienting effects of microgravity. The complexity of this logistics chain is often overlooked. It was not just about building something in space. It was about managing a continuous flow of people, hardware, and supplies from Earth to a construction site 250 miles above the planet, moving at 17,000 miles per hour. This required a global support network of launch facilities, control centers, and manufacturing plants, all working in sync for over a decade. The success of the International Space Station stands as a testament to this incredible logistical and engineering feat. proving that humanity can orchestrate a project of such scale and precision in the most hostile environment imaginable. The lessons learned from this assembly process are now being applied to plans for future stations around the Moon and Mars, where the logistics will be even more challenging due to the greater distances and communication delays. So, the next time you see a picture of the completed station, remember that it is not just a spacecraft. It is a symbol of persistent, precise, and international effort, a collection of parts launched separately and fused together in orbit with an accuracy that defies belief. But all that precise assembly often required astronauts to venture outside the station, into the deadly void of space, in a process known as spacewalking, which is perhaps the most dangerous aspect of building and maintaining a space station. Every time an astronaut steps out of the airlock, they are entering an environment where a single small error can be fatal, turning a routine maintenance task into a life or death situation. The spacesuit they wear is not just clothing. It is essentially a personal spacecraft, a complex system designed to protect them from the vacuum, extreme heat, and freezing cold. These suits have multiple layers: an inner cooling garment, a pressure bladder, and a tough outer shell to resist micrometeoroids. They provide oxygen for breathing, remove carbon dioxide, regulate temperature, and manage moisture, all while allowing some mobility. But despite this engineering marvel, the suit is the only thing standing between the astronaut and instant death. A puncture, even one as tiny as a pinhole from a sharp edge or a piece of debris, could lead to rapid decompression. In such an event, the air inside the suit would rush out into space, causing the pressure to drop dangerously fast. An astronaut might have only seconds to recognize the problem and activate emergency procedures before losing consciousness due to hypoxia, and death would follow shortly after. This ever-present risk means that every spacewalk is planned with multiple redundancies and checks, but the threat is always lurking. Beyond the suit itself, the environment is filled with invisible dangers. Space debris is a constant concern. Millions of fragments from old satellites, spent rocket stages, and other missions orbit the Earth at incredible speeds, some as small as a paint flake but travelling at over 28,000 kilometers per hour. At that velocity, even a tiny piece carries kinetic energy greater than a rifle bullet, and an impact could easily penetrate the suit or damage critical components on the station. While the station has shields designed to absorb smaller impacts, larger objects are tracked by ground radar, and the station may perform maneuvers to avoid them. However, many debris pieces are too small to be monitored, creating an unpredictable hazard that astronauts simply have to accept as part of the job. The physical demands of a spacewalk are another major challenge. The suit is bulky and pressurized to about a third of Earth's atmospheric pressure, which makes it stiff and difficult to move. Simple actions like gripping a tool or turning a handle require significant muscle effort, and astronauts often compare it to working inside an inflated balloon. This constant exertion leads to rapid fatigue, which can impair judgment and coordination over time. Hands and arms can become sore from fighting the suit's resistance, and the physical strain is compounded by the mental stress of knowing that a mistake could be catastrophic. To prepare for this, astronauts undergo extensive training in neutral buoyancy labs, which are giant pools where they practice tasks in simulated weightlessness. But even the best training cannot fully replicate the conditions of space, where there is no buoyancy to help support the suit's weight, and every movement has consequences in a frictionless environment. Time is a critical constraint during spacewalks. Each outing is limited by the suit's consumables. The oxygen supply, battery power, and cooling water typically last for about 6 to 8 hours. This means that tasks must be meticulously planned and executed efficiently, with little room for error or delay. If an unexpected problem arises, astronauts may have to make quick decisions without direct input from mission control due to communication delays. Even though the station is in low Earth orbit, signals can take a few seconds to travel to Earth and back, which might not seem like much, but in an emergency, those seconds can feel like an eternity. Astronauts are trained to be highly autonomous, following protocols and relying on their instincts and teamwork. The process of preparing for a spacewalk itself is lengthy and rigorous. Hours before exiting the airlock, astronauts breathe pure oxygen to purge nitrogen from their bloodstream, reducing the risk of decompression sickness, also known as the bends. Once suited up, they undergo final checks before the airlock is depressurized, a slow and careful process to ensure no leaks. During the spacewalk, they are tethered to the station at all times to prevent drifting away, and they use handholds and foot restraints to anchor themselves while working. The psychological aspect cannot be overlooked. Floating in the void with nothing but a thin layer of material between you and the infinite darkness is both awe-inspiring and terrifying. The view of Earth is breathtaking, but it also serves as a reminder of how far from home they are. Isolation and the constant awareness of risk can weigh heavily on the mind, requiring mental resilience and focus. Historical incidents highlight these dangers. For example, on a past mission, an astronaut experienced a small water leak in his helmet, which could have led to drowning if not addressed quickly. Such events reinforce the need for vigilance and continuous improvement in suit design and procedures. Despite all precautions, spacewalks remain one of the most hazardous activities in human spaceflight, a testament to the courage and skill of those who undertake them. They are essential for assembly, repairs, and scientific experiments, but each one is a calculated risk that underscores the fragility of human life in space. As we look to future missions to the Moon and Mars, the lessons learned from these extravehicular activities will be crucial for developing safer technologies and protocols. But the fundamental dangers of venturing into the vacuum will always be present. The bravery of astronauts who face these perils enables the continued operation and expansion of our presence in space, making each successful spacewalk a triumph of human ingenuity and endurance over one of the most hostile environments imaginable. The complexity of managing these risks involves international collaboration, with teams on the ground monitoring every aspect and providing support. From the moment the airlock opens to the final safe return, every second is accounted for, and every movement is deliberate. The suits are constantly evolving, with new materials and systems being tested to enhance safety and mobility. For instance, newer designs aim to be more flexible and include advanced life support systems that can handle longer durations. However, the core challenges remain: the vacuum, radiation, debris, and human physical limits. In the end, spacewalks are a necessary part of space exploration, but they are never taken lightly. They represent the extreme edge of what humans can do in space, where precision, training, and a bit of luck come together to achieve the impossible. As we continue to build and maintain structures like the International Space Station, the knowledge gained from each spacewalk helps pave the way for future endeavours, reminding us that the quest to explore the cosmos is fraught with peril but driven by an unyielding spirit of discovery. The astronauts who perform these feats are not just engineers or scientists, they are pioneers stepping into the unknown, and their contributions are vital to our understanding and utilisation of space. So, while we marvel at the technological achievements, let us not forget the human element, the individuals who risk everything to push the boundaries of what is possible, one careful step at a time into the void. After facing the immediate dangers of spacewalks, astronauts return to the relative safety of the station, but the station itself is locked in a perpetual battle against the fundamental hostility of space, starting with the vacuum. The vacuum of space is not just empty. It is a profound nothingness that presents a constant threat. There is no air to breathe, which is obvious, but the implications go far beyond that. Without an atmosphere, there is no medium to conduct heat away from the station, meaning that heat generated by electronics, human bodies, and experiments cannot dissipate through convection or conduction like it does on Earth. This makes managing temperatures incredibly difficult, as heat simply builds up unless actively removed. Additionally, the vacuum offers no protection from radiation. On Earth, our atmosphere and magnetic field shield us from the constant barrage of cosmic and solar radiation. But in orbit, the station and its crew are fully exposed. This radiation can pierce through the station's walls, damaging sensitive electronics over time and increasing the long-term cancer risk for the astronauts on board. It is an invisible, insidious danger that requires heavy shielding and careful monitoring. But complete protection is impossible, so radiation exposure is a calculated risk of spaceflight. Compounding this is the extreme temperature swings that the station endures. As it orbits the Earth every 90 minutes, it experiences a brutal thermal cycle. The side facing the Sun is blasted with direct solar radiation, heating the external surfaces to temperatures exceeding 120 degrees Celsius. Meanwhile, the side in the shadow of the Earth plunges into darkness, where temperatures can drop to below minus 150 degrees Celsius. This is not a gradual change. The transition from blistering heat to deep cold happens rapidly as the station moves in and out of sunlight. Imagine taking a metal object and repeatedly heating it in a furnace, and then dunking it in liquid nitrogen every hour and a half. That is the kind of stress the station's materials undergo. This cyclical heating and cooling causes expansion and contraction in the metal alloys, composites, and seals that make up the station's structure. Over time, this thermal fatigue can lead to microcracks, material weakening, and potential failures if not accounted for in the design. Every component on the outside of the station, from solar panels to scientific instruments, must be built to withstand this relentless punishment. The solar arrays, for example, are designed to flex and tolerate these temperature changes without shattering or losing efficiency. The coatings on the station's exterior are specially formulated to reflect or absorb heat as needed, helping to manage the thermal load. But the challenge does not stop at the hull. Managing the internal environment is a constant engineering struggle. The station must maintain a shirt-sleeve environment for the crew, which means keeping the air breathable, the temperature comfortable, and the humidity controlled, all while the outside environment tries to disrupt this balance. The thermal control system is a complex network of loops filled with ammonia, which absorbs heat from the interior and carries it to radiators located on the outside. These radiators are positioned on the cold side of the station to efficiently dump the heat into space. However, this system must be incredibly robust because a failure could lead to overheating inside within hours. The vacuum also affects how sounds travel, or rather, how they do not. Without air, there is no sound transmission, so the outside of the station is perpetually silent. But inside, the constant hum of machinery is a reminder of the life support systems working overtime to keep the environment stable. Another aspect of the vacuum is its effect on materials. In the absence of oxygen, some materials that would normally oxidize or rust on Earth behave differently, but outgassing can occur, where volatile chemicals evaporate from materials, potentially contaminating sensitive instruments or the cabin air. This requires careful selection of materials used in construction to minimize these effects. The temperature extremes also impact the station's orientation. To manage heat, the station often flies in a specific attitude, with the radiators pointed towards the dark void of space and the solar panels angled towards the sun. This requires constant adjustments using gyroscopes and thrusters, consuming fuel and energy. The crew must be aware of these orientations, especially during spacewalks, to avoid being on a surface that is dangerously hot or cold. The psychological effect of knowing that just a few inches away, beyond a thin layer of metal, is the environment that would kill you instantly is something astronauts learn to live with. But it underscores the fragility of their habitat. The development of the station's thermal protection system involved extensive testing on Earth, using thermal vacuum chambers that simulate the space environment. These tests were crucial for verifying that components could survive the transitions. But real-world conditions always present surprises. For instance, the accumulation of space dust or debris on surfaces can alter their thermal properties, absorbing more heat or making radiators less efficient. Maintenance and inspections are necessary to monitor for any damage caused by thermal stress. The windows on the station are a great example of this engineering challenge. They are made of multiple panes with gaps to reduce heat transfer, and they must withstand the temperature swings without cracking or fogging. Over the years, some windows have become pitted and scratched by micrometeoroids, which can further complicate thermal management. The constant battle against the vacuum and temperature extremes is a testament to human ingenuity, but it also highlights the limits of current technology. As we plan for missions beyond low Earth orbit, to the Moon or Mars, the environments will be even harsher, with longer periods of darkness and exposure to radiation, requiring new solutions. For now, the International Space Station remains a shining example of what we can achieve, a habitable island in a sea of hostility, but it requires unending vigilance and a complex, energy-intensive infrastructure to keep it that way. The systems in place are redundant and reliable, but they are not infallible, and the crew is trained to respond to emergencies, such as a cooling loop failure, which could quickly become life-threatening. In essence, the station is not just a laboratory, it is a lifeboat in the void, and every day it survives is a victory against the relentless forces of space. The knowledge gained from managing these challenges is invaluable for future spacecraft design, where weight and power constraints will be even tighter. So, while we marvel at the scientific output and the international cooperation, let us not forget the silent, constant war being waged against the vacuum and temperature, a war fought with pumps, radiators, and smart engineering, ensuring that humanity has a foothold in the cosmos. This ongoing struggle defines the very nature of living in space, where comfort is a hard-won achievement and the environment is always waiting for a single mistake to reclaim its territory. The vacuum and temperature extremes are not just background conditions. They are active adversaries that shape every aspect of mission planning, design, and daily operations, reminding us that space is anything but empty. It is full of challenges that demand our utmost respect and innovation. While the station is engineered to withstand the vacuum and brutal temperature swings, there is another invisible and ever-present threat whizzing around it at unimaginable speeds: space junk. The orbit around Earth is not a pristine highway. It is a cluttered junkyard filled with millions of pieces of debris from decades of space exploration. This includes everything from defunct satellites and spent rocket stages to tiny fragments from explosions or collisions, even flakes of paint that have broken loose over the years. The problem with this debris is not its size, but its velocity. Each piece is orbiting the planet at roughly 28,000 kilometers per hour, a speed necessary to maintain orbit, but which turns the smallest speck into a potentially devastating projectile. At that velocity, a piece of debris the size of a marble carries more kinetic energy than a high-powered rifle bullet, and something as small as a fleck of paint can chip or crack a heavily reinforced window. The energy released upon impact is immense because it is a function of speed squared, meaning that even low-mass objects become incredibly destructive. This makes every piece of debris, no matter how small, a serious threat to the structural integrity of the station. A direct hit on a pressurized module could cause a rapid depressurization, endangering the lives of the crew inside within minutes. An impact on a critical system, like a solar panel or a radiator, could cripple the station's power or thermal management, leading to a cascade of failures. The windows on the station are particularly vulnerable. They are made of multiple layers of strong glass, but they are still susceptible to pitting and cracking from tiny impacts, which is why they are regularly inspected and replaced if necessary. To protect against this, the station is equipped with special shields known as Whipple shields. These are not solid plates of armour. That would be too heavy. Instead, they are clever multi-layered shields where a thin outer bumper is spaced away from the main hull. The idea is that when a small piece of debris hits the bumper, it vaporizes upon impact, spreading the energy of the collision over a larger area of the inner wall, which can then absorb the force without being punctured. This design is highly effective against smaller debris, but it is not a perfect solution for larger objects. For larger, trackable pieces of junk, the station relies on a global network of radar and telescopes to monitor their paths. When a piece of debris is predicted to come within a certain distance of the station, a safety threshold that is constantly evaluated, Mission Control can decide to perform a debris avoidance maneuver. This involves using the thrusters on the station itself or on a docked spacecraft, like a Russian Progress vehicle, to fire gently and push the entire complex into a slightly different orbit, just enough to avoid the potential collision. These maneuvers are not rare. They happen several times a year and require precise calculations and coordination. However, this system has significant limitations. The tracking networks can only reliably monitor objects down to about the size of a softball. There are millions of smaller fragments, from the size of a nut or bolt down to tiny shards, that are simply too small to be tracked consistently. These objects represent a constant, unpredictable risk. The crew on board is aware that, at any moment, an unseen piece of debris could strike, and there would be no warning. This is the reality of living in low Earth orbit. It is a calculated risk that is accepted but never ignored. The source of all this junk is decades of space activity. Early space missions often left their rocket stages in orbit, and satellites were abandoned at the end of their lives. Accidental collisions have made the problem much worse. For example, in 2009, a defunct Russian satellite collided with an active American communications satellite, creating thousands of new pieces of debris in an instant. Anti-satellite tests, where countries deliberately destroy their own satellites, have also contributed massive clouds of fragments. Each new breakup event adds to the population, increasing the risk for all spacecraft in similar orbits. This creates a cascading effect known as the Kessler syndrome, a theoretical scenario where the density of objects in orbit becomes so high that collisions between them generate more debris, leading to a runaway chain reaction that could make certain orbital regions unusable for generations. While we are not there yet, the concern is real and drives international efforts to mitigate the problem. Guidelines now exist for satellite operators to design their spacecraft for end-of-life disposal, either by deorbiting them to burn up in the atmosphere or by moving them to a graveyard orbit away from busy regions. But enforcing these guidelines is challenging, and not all countries or private companies comply. The problem is also self-perpetuating, as more satellites are launched, particularly with large constellations of thousands of small satellites for internet services. The potential for collisions increases, even if each satellite is designed to be deorbited. The station itself contributes to the problem in a small way. During spacewalks, astronauts have to be extremely careful not to lose any tools or equipment, as anything that drifts away becomes new space junk. Even the waste disposal system is designed to minimize debris. Trash is packed into uncrewed cargo vessels, which are then sent to burn up in the atmosphere, rather than being jettisoned into orbit. The long-term solution requires active debris removal, missions that would go up and capture large defunct objects and bring them down. But this technology is still in its early stages and is incredibly expensive. For now, the International Space Station and its crew must live with this daily threat, a reminder that humanity's footprint in space includes a messy and dangerous legacy. The psychological impact on astronauts is non-trivial. Knowing that an invisible, high-speed object could strike at any time adds a layer of stress to an already high-stakes environment. They conduct regular drills for emergency scenarios, including a rapid shelter-in-place procedure where they retreat to the more robustly shielded Soyuz or Crew Dragon spacecraft that are docked to the station. ready for an emergency return to Earth if a significant impact occurs and the station is compromised. The sound of an impact alarm is one of the most chilling sounds an astronaut can hear, prompting an immediate assessment of the situation. Fortunately, such serious events have been rare, but minor impacts are detected on the exterior regularly, evidenced by the pockmarks and scratches found on surfaces during inspections. The challenge of space junk is a global one, requiring international cooperation for tracking, data sharing, and regulation. No single country can solve it alone. As we look to the future and plan for new space stations, lunar bases, and missions to Mars, the lessons learned from dealing with debris around the ISS will be critical. Future spacecraft will likely need even more advanced shielding and autonomous collision avoidance systems. The problem of space junk underscores a broader issue: our responsibility to manage the orbital environment we are increasingly dependent on for communications, navigation, and science. It is a classic tragedy of the commons, where individual actions collectively create a hazard for all. Addressing it will require not just technological innovation, but also diplomatic and policy efforts to ensure the sustainable use of space. For the astronauts on the station, it is a tangible danger they orbit through 16 times a day, a cloud of shrapnel from our own making the achievement of maintaining a human presence in space all the more remarkable. Every day without a catastrophic impact is a success, but the risk is always there, a silent testament to the challenges that come with venturing beyond our planet. The continued operation of the ISS in this environment is a tribute to the robustness of its design and the vigilance of the teams on the ground, but it is a constant battle against an adversary of our own creation. As more objects are launched, the problem only intensifies, making the development of effective debris removal technologies one of the most pressing priorities for the future of spaceflight. Until then, the station will continue its dance through the orbital junkyard, a symbol of human achievement navigating a sea of our own discarded hardware. Keeping a station safe from debris is one thing, but powering it and keeping it from overheating are constant, interconnected battles that define its very ability to function. The International Space Station is a massive power hog, demanding a continuous and immense supply of electricity to run everything from the supercomputers and scientific freezers preserving priceless experiments to the simple light bulbs and coffee machine that make life bearable for the crew. Its primary source of energy is the sun, harnessed by those giant solar arrays that stretch out from the main truss like wings. These arrays are not static. They are designed to rotate and tilt, constantly tracking the sun to maximize energy capture as the station speeds around the Earth every 90 minutes. This sun tracking is a complex dance, ensuring the panels face the sunlight directly even as the station's attitude changes for other operations, like communications or thermal control. The electricity generated by these photovoltaic cells is then conditioned and distributed throughout the station's complex electrical grid, powering a small city's worth of equipment 24 hours a day. But here is the catch. Generating all that electricity creates a huge amount of waste heat. On Earth, you could rely on air convection or simply radiate heat into the atmosphere. But in the vacuum of space, there is no air to carry heat away. This means that all the heat generated by the electronics, the astronauts' bodies, and the experiments themselves has to be managed actively and deliberately, or the interior would quickly become an uninhabitable oven. This is where the station's sophisticated thermal control system comes into play, a network that is as vital as the power system itself. The system uses a two-stage process to manage heat. Inside the pressurized modules, a loop of water circulates through the walls and past heat exchangers, collecting excess heat from the cabin air and from specific high-power equipment. This water loop, kept separate from the drinking water, then transfers its accumulated heat to a second, external loop through a series of heat exchangers. This external loop uses liquid ammonia as its coolant, chosen because it has a much lower freezing point than water. which is essential for the frigid conditions on the station's dark side. The ammonia is pumped through large radiators, those distinctive white panels attached to the station's truss. These radiators are always oriented away from the sun, towards the cold blackness of space, where they can efficiently radiate the collected heat as infrared energy. The entire system is a masterpiece of plumbing and engineering, with miles of tubing, dozens of pumps, and sophisticated controls that constantly monitor temperatures and adjust flow rates. The reliability of this system is absolutely non-negotiable. A single major failure in the thermal control system, such as a pump failure or a leak in the ammonia loop, would lead to a rapid and uncontrollable rise in internal temperature. Within hours, conditions inside the station could become lethal, forcing the crew to abandon ship in their lifeboats, the docked Soyuz or Crew Dragon spacecraft. This is why there is so much redundancy built into the design. Multiple pumps are available, and the system has isolated segments so that a failure in one section can be bypassed. The astronauts train extensively for scenarios involving cooling system failures, and they have performed several complex spacewalks to repair and replace components of the external ammonia loops. The interplay between power and thermal management is a delicate balance. The more power the station uses, the more heat must be rejected. If the radiators are not properly positioned, or if they become damaged by space debris, their efficiency drops, forcing a reduction in power consumption to prevent overheating. This could mean turning off non-essential experiments or systems, a trade-off that mission controllers are constantly evaluating. The station's orientation, or attitude, is frequently adjusted not just for solar power generation but also for thermal reasons. A careful compromise between pointing the solar arrays at the sun and pointing the radiators into the darkness. The solar arrays themselves are vulnerable. They degrade over time due to radiation and impacts from micrometeoroids, gradually producing less power. This natural decay is factored into the station's long-term planning, but it means that the margin between available power and required power slowly shrinks over the years. The energy is stored in large batteries for use when the station is in Earth's shadow. During the 45-minute night portion of each orbit, these batteries have been upgraded over the station's lifetime, with newer, more efficient lithium-ion batteries replacing older models during a series of spacewalks. The process of storing and discharging this energy also generates significant heat, which further adds to the thermal load that the system must handle. Managing all of this requires a constant, real-time dialogue between the station's onboard computers and flight controllers on the ground in Houston and Moscow. They monitor every volt, every amp, and every degree of temperature, ready to respond to any anomaly. The system is so robust that it has supported continuous human habitation for over 2 decades, but it is never taken for granted. It is a loud, humming, vibrating testament to human engineering, a complex dance of energy conversion and heat rejection that happens silently and automatically, out of sight and out of mind for most people, but it is the very heartbeat of the station. Without this meticulously balanced system of power generation and thermal management, the station would be nothing more than a silent, frozen, and dark metal tomb drifting in the void. The lessons learned from operating this system are directly informing the design of future spacecraft for lunar and Martian missions, where the energy and thermal challenges will be even greater due to longer nights, greater distances from the sun, and the need for even more reliability. For now, the sight of the International Space Station gliding across the night sky is a promise kept alive by this incredible technological symphony, a beacon of light powered by the sun and cooled by the cold of space itself. A perfect example of humanity's ability to create a sustainable pocket of life in the most inhospitable of environments. The constant need for power and the critical task of dumping heat are not just engineering problems. They are the fundamental requirements for existence in space, and the station systems have proven that we can meet those requirements. but only through relentless innovation, vigilance, and a deep understanding of the harsh physics that govern the orbital environment. Every watt of power and every joule of heat managed successfully is a small victory in the ongoing mission to maintain our foothold in space, a process that continues unabated, every second of every day, ensuring that the lights stay on and the air remains breathable for the astronauts who call the station home. This intricate balance between energy in and heat out is the unsung hero of the space station's story, a background process that enables all the groundbreaking science and international cooperation that we celebrate, a silent, efficient, and absolutely vital engine of survival. While the station's power and thermal systems form a vital backbone, the true marvel of engineering lies in the systems that directly keep the crew alive, the incredibly complex life support systems that create a miniature, self-sustaining ecosystem in the void. This is not just about having air and water. It is about continuously recycling and regenerating them in a completely closed loop, a challenge that pushes the limits of our technology. On Earth, we take for granted the natural cycles that purify our air and water, but in space, we have to replicate those processes mechanically, and the margin for error is virtually zero. The air system is the most immediate concern. Astronauts breathe in oxygen and exhale carbon dioxide, and if that CO2 is not removed from the cabin air, it would build up to toxic levels, leading to headaches, confusion, and eventually death. To prevent this, the station uses a system called the Carbon Dioxide Removal Assembly, which uses a material called zeolite to scrub the CO2 from the air. The captured carbon dioxide is not just wasted, it can be vented overboard, but there are also experiments and systems aimed at converting it into something useful, like water or even methane, though the primary goal is simply to keep the air safe. But removing CO2 is only half the battle. You also have to replenish the oxygen that the crew consumes. This is done through a process called electrolysis, where water is split into hydrogen and oxygen using electricity. The oxygen generation system takes water, often from the recycled supply, and produces breathable oxygen for the crew, while the hydrogen is either used in other processes or vented into space. This creates a delicate balance between the water and air systems, as oxygen production consumes water. Now, let's talk about water, which is an even more precious resource. Every drop of water on the station is accounted for and recycled. This includes moisture from the air, urine from the crew, and even sweat. The water recovery system is a complex assembly of filters, chemical processes, and distillation units that turn wastewater back into pure, drinkable water. The process involves multiple stages. First, the water is filtered to remove large particles. Then it goes through a series of chemical treatments to break down contaminants and kill bacteria. And finally, it is distilled to remove any remaining impurities. The result is water that is actually purer than what most people drink on Earth, though astronauts often say it tastes a bit flat, likely due to the lack of minerals. The psychological hurdle of drinking water that was, just hours before. Someone's urine is something crews have to overcome. But the system's reliability is proven. Without this recycling, the logistics of supplying water from Earth would be astronomical. Just to give you an idea, each astronaut needs about 2 litres of water per day for drinking alone, plus more for hygiene and food preparation, over a year. For a crew of 6, that would amount to thousands of litres, each kilogram of which costs thousands of dollars to launch. The recycling system recovers about 90% of the water, dramatically reducing the need for resupply missions. However, these systems are mechanically and chemically complex, with countless pumps, sensors, and filters that can and do fail. Maintenance is a constant task for the crew, who must replace filters, clean components, and troubleshoot problems, often with guidance from mission control. A failure in the water system could lead to contamination or a shortage, while a failure in the air system could have more immediate and dire consequences. The systems are designed with redundancies, but a major breakdown could force the crew to rely on emergency supplies or even consider an evacuation if it cannot be fixed quickly. The complexity extends to monitoring. The air and water are continuously sampled and analysed for contaminants, as any build-up of trace gases or bacteria could be harmful in a sealed environment. The crew also has to manage their waste, including solid waste, which is compacted and stored for disposal in cargo vehicles that burn up on re-entry. The life support systems are essentially trying to mimic the functions of Earth's biosphere on a very small scale, but without the billions of years of evolution that made our planet's systems so resilient. This is a testament to human ingenuity, but it also highlights our dependence on these technological crutches for survival in space. Every system is interconnected. A problem in the power supply could affect the oxygen generator, and a leak in the water system could impact both drinking water and oxygen production. The astronauts train extensively to handle emergencies related to life support, from fixing a faulty pump to isolating a module in case of air contamination. The sounds of the life support systems, the hum of fans, the gurgle of water are the constant background noise of life on the station, a reminder of the fragile bubble of habitability they inhabit. As we look to longer missions, to the Moon and Mars, the need for even more closed-loop systems becomes critical, because resupply from Earth will be impossible for months or years at a time. The systems on the ISS are a testing ground for these future technologies, and they have already taught us invaluable lessons about reliability and efficiency. For instance, newer systems are being developed that aim to recycle even more water and air, and to integrate plant growth for additional oxygen and food production. However, the challenges remain daunting. The systems are heavy, power-hungry, and require regular maintenance from the crew, which takes time away from scientific research. Despite all the technology, the human element is crucial. The crew must be vigilant about conserving resources and reporting any anomalies immediately. A small leak or a strange odour could be the first sign of a bigger problem. The international collaboration on the station means that life support components come from different countries, each with their own engineering standards, which adds another layer of complexity to integration and maintenance. In the end, the life support systems are the unsung heroes of the space station, working tirelessly in the background to turn a metal shell into a home. They represent one of the greatest engineering achievements in history, allowing humans to live and work in an environment that is fundamentally hostile to life. Every breath the crew takes and every sip of water they drink is a testament to the success of these systems, a daily miracle of recycling and regeneration that enables humanity's continuous presence in space. The knowledge gained here is paving the way for future explorers to venture farther into the solar system, carrying with them the promise of self-sustaining habitats that can keep them alive on the long journey to new worlds. It is a slow, steady, and often overlooked process, but it is the foundation upon which all other space activities are built. Without these complex systems, the station would be just another piece of debris, and the dream of living in space would remain just that, a dream. So, the next time you see the station pass overhead, remember that inside that tiny speck of light, a sophisticated mechanical lung and kidney are hard at work, recycling the very essence of life itself, enabling a handful of people to call the vacuum of space their temporary home. This ongoing effort to create a closed ecosystem is not just about survival, it is about learning to thrive beyond Earth. And each day of operation is a step towards a future where humanity is no longer confined to a single planet. The systems are not perfect, and they require constant care, but they are a shining example of what we can achieve when we apply our collective intelligence to the problem of keeping humans alive in the most unforgiving of environments. The air may be manufactured and the water recycled, but the life they support is very real, and the science conducted under their protection will help ensure that life can continue to reach for the stars. But all those intricate life support systems and the daily scientific work are utterly dependent on one critical thing: a constant, reliable conversation with Earth. The International Space Station is in a perpetual dance with our planet, and staying connected is a complex ballet of technology and timing. The station does not have a single, permanent phone line home. Instead, it relies on a sophisticated network of satellites and ground-based antennas to maintain contact with mission control centers in Houston, Moscow, and other locations around the world. This system is necessary because the ISS moves at an incredible speed, completing an orbit every 90 minutes, which means it is constantly passing over different parts of the Earth and frequently moving out of the direct line of sight of any one ground antenna. To solve this, NASA uses the Tracking and Data Relay Satellite System, a constellation of geosynchronous satellites that act as relays, bouncing signals from the station down to ground stations and vice versa. This creates a nearly continuous communication link, but it is not perfectly seamless. The handover between satellites or between a satellite and a ground station can sometimes introduce brief moments of signal loss or degradation, which are generally planned for and expected, but they still require systems to be robust enough to handle these interruptions. The communication link carries everything: voice calls between the crew and mission control, vital telemetry data from every system on the station, commands sent up from the ground, and even the video feeds we all enjoy from space. This constant flow of information is the nervous system of the entire operation, allowing engineers on the ground to monitor the health of the station and the crew in real time. However, there is a fundamental physical limitation that cannot be overcome: the speed of light. Even though the station is relatively close in astronomical terms, only about 400 kilometers high, the signals still have to travel that distance up to a satellite and then down to Earth, or directly to a ground station when possible. This round-trip time results in a slight delay, typically between 1 and 3 seconds. Now, a few seconds might not sound like much when you are having a casual conversation. You can still talk to the astronauts, and there is just a slight pause before they respond, similar to a bad international phone call. But for critical operations, that delay is a game changer. It makes real-time remote control of systems impossible. Imagine if a warning light came on indicating a pressure leak or a fire. By the time the data reached mission control and the engineers assessed the situation and sent a command back, several precious seconds would have passed. In an emergency, those seconds can mean the difference between a contained incident and a catastrophe. This is why the astronauts on board are trained to be highly autonomous. They are not just passengers following orders from the ground. They are resident experts, engineers, and first responders. They undergo years of training, simulating hundreds of failure scenarios, so that when a problem arises, they can assess the situation and execute pre-established procedures without waiting for instructions. The ground team provides crucial support and analysis, but the immediate actions are in the hands of the crew. This autonomy extends to complex repairs, medical emergencies, and even the daily operation of scientific experiments. The communication delay also affects how spacewalks are conducted. While astronauts are outside, they are in constant communication with a capsule communicator inside the station and with mission control, but the delay means that conversations are slightly staggered. The astronauts must often describe what they are seeing and what they plan to do, and then wait a moment for confirmation or advice. This requires a great deal of patience and clear, precise communication from both ends. Another common event is the scheduled loss of signal, which occurs when the station flies over parts of the Earth where there are no ground stations and it is temporarily out of range of the relay satellites. These periods can last for up to 40 minutes at a time, and while they are planned and the station is designed to operate autonomously during these passes, it can still be a stressful time for the crew. They know that if something goes wrong, they are entirely on their own until contact is re-established. The psychological impact of this intermittent isolation, coupled with the inherent risk of their environment, should not be underestimated. The communication system itself is a complex piece of engineering that requires constant maintenance and upgrades. The antennas on the station must be precisely pointed, and the software that manages the data flow must be incredibly robust to handle the vast amounts of information. Interference from solar activity or technical glitches can also disrupt communications, adding another layer of uncertainty. Furthermore, the station is an international partnership, so the communication protocols must integrate systems from different countries, which can have different technical standards and procedures. This requires extensive coordination and testing to ensure compatibility. As we look to future missions beyond low Earth orbit, to the Moon and Mars, the communication delay will become a much more significant factor. A round-trip signal to the Moon can take around 2.5 seconds, and to Mars, it can vary from several minutes to over 20 minutes depending on the planet's positions. This will make real-time guidance from Earth completely impossible for many operations, forcing an even greater level of crew autonomy and requiring spacecraft systems to be far more independent and self-healing. The experience gained from operating the ISS under its slight but significant delay is therefore invaluable. It is teaching us how to build procedures and technologies for a future where astronauts will be truly on their own for long periods. The reliance on a communication link that is not always instantaneous adds a fundamental layer of risk to every activity on the station. It means that every system must be designed with the assumption that help is not immediately available, and that the humans on board are the final and most important line of defense. This shapes the entire culture of spaceflight, emphasizing training, redundancy, and the critical role of human judgment. So, while we marvel at the live videos and the conversations from space, it is important to remember the fragile, delayed thread that connects the station to Earth, and the incredible responsibility that rests on the shoulders of the astronauts who live and work at the other end of that line. The communication system is a lifeline, but it is a stretched and elastic one, and learning to work within its constraints is a core skill for living in space. Every day, the success of the mission depends on the smooth flow of data across that gap, a testament to both technological achievement and human adaptation. The quiet hum of the communication system is the sound of home, a constant reminder of the connection to Earth, but also a reminder of the distance and the delay that defines the reality of orbital life. This ever-present challenge of staying in touch underscores the isolation of space and the resilience required to thrive there, making every clear signal a small victory in the ongoing effort to maintain a human presence beyond our planet. While the challenges of communication delays force the station's crew to be self-reliant, the very structure they inhabit is engaged in a silent, slow-motion battle against the relentless forces of the space environment, a process of material degradation that never stops. The materials used to build the International Space Station are not immune to the passage of time. In fact, they face unique and aggressive conditions that cause them to wear out in ways we rarely see on Earth. This is not like a car rusting in a rainy climate. It is a multi-front assault from radiation, extreme temperature swings, and microscopic impacts that test the limits of modern engineering. The most pervasive threat is radiation. The station is constantly bombarded by ultraviolet radiation from the sun and cosmic radiation from deep space. This radiation is incredibly damaging to many materials, especially polymers and composite materials. Over time, the energetic particles break down the molecular chains in these materials, making them brittle and causing them to lose their flexibility and strength. You can see this effect on the station's exterior, where some materials have become faded and discolored, a clear sign of radiation damage. This embrittlement is a serious concern because components that need to be slightly flexible, like seals or cable insulation, can crack and fail, leading to potential leaks or electrical problems. It is a slow, invisible process that steadily weakens the station from the outside in. Then there are the thermal cycles. As the station orbits the Earth every 90 minutes, it swings from blistering heat in direct sunlight to profound cold in the shadow of the planet. This cycle repeats itself over 16 times a day after day, year after year. Metals and other materials expand when heated and contract when cooled. This constant expansion and contraction, over thousands and thousands of cycles, induces something called thermal fatigue. Imagine bending a paperclip back and forth repeatedly. Eventually, it will snap due to metal fatigue. The same principle applies to the station's structure on a massive scale. This stress can lead to the development of microcracks in metal alloys and joints. These cracks are tiny at first, but they can grow over time, potentially compromising the structural integrity of a module or a critical bracket. Predicting exactly where and when these cracks will form is incredibly difficult, as it depends on the specific material, its manufacturing history, and the exact thermal loads it experiences. Another constant source of wear is the bombardment by micrometeoroids and orbital debris. Even though most of these particles are smaller than a grain of sand, they are travelling at orbital velocities, which means they hit with tremendous energy. The station's windows are a prime example of this. They are made of multiple layers of high-strength glass, but over the years, they have become pitted and scratched by countless tiny impacts. This gradual degradation can reduce optical clarity, which is important for observations and for the crew's morale, as the view of Earth is a precious commodity. While the windows are designed to be replaced, the constant sandblasting effect is a reminder of the abrasive nature of the space environment. This impact damage is not limited to windows. It affects solar panels, radiator surfaces, and external coatings. A scratched or pitted radiator surface is less efficient at dumping heat, and a damaged solar panel generates less power. So even these small impacts can have a cumulative effect on the station's overall performance. Corrosion is another factor. Though it might seem counterintuitive in the vacuum of space, inside the station, in the controlled atmosphere, corrosion can still occur. Moisture from the air, along with trace contaminants, can lead to the oxidation of metals over time. While the environment is carefully managed, it is impossible to eliminate all potential sources of corrosion, especially in hard-to-reach areas or around connectors and fasteners. This is why material selection was so critical during the station's design. Engineers had to choose alloys and coatings that would resist corrosion in this unique enclosed environment. The combined effect of all these factors, radiation, thermal cycling, impact damage, and internal corrosion, makes predicting the long-term behaviour of materials a highly uncertain science. Engineers on the ground use complex models and data from material samples exposed to space for years, but there is always an element of surprise. The station is a living laboratory for material science, and the data it provides is invaluable for designing future spacecraft that will need to last even longer, perhaps on journeys to Mars. To manage this inevitable wear and tear, a rigorous schedule of inspection and maintenance is essential. Astronauts perform regular internal and external inspections, using cameras and their own eyes to look for signs of damage, such as cracks, discoloration, or debris impacts. They have detailed checklists and are trained to identify potential problems. When issues are found, repairs are undertaken, which can range from simple cleaning or tightening of bolts to complex spacewalks to replace a damaged component. The philosophy is one of preventive maintenance. The goal is to identify and address problems long before they become critical failures. This requires a massive inventory of spare parts on the ground and a well-organised logistics system to launch replacements when needed. The ageing of the station's materials also influences the planning for its eventual decommissioning. Engineers must consider the accumulated fatigue and damage when calculating how to safely guide the station through a controlled re-entry. The knowledge gained from studying material degradation on the ISS is directly applied to new space stations being planned, like those intended for lunar orbit. For these future outposts, materials will need to be even more robust to withstand the different radiation environment and temperature extremes of deep space. Research is ongoing into new materials, such as self-healing polymers or advanced composites with better radiation resistance. In the meantime, the International Space Station continues to serve, its materials slowly but surely succumbing to the environment it was built to conquer. It is a testament to the quality of its original construction that it has lasted as long as it has, but it is also a reminder that nothing in space is permanent. The constant vigilance required to monitor and maintain its structure is a major, ongoing effort that involves thousands of people on the ground and a brave crew in orbit. So, while we often focus on the groundbreaking science and the human stories from the station, we should not forget the silent, slow battle being waged by its very bones and skin against the relentless forces of space. This material fatigue is a fundamental challenge of long-duration spaceflight, one that will accompany us on every step of our journey into the solar system. Understanding and overcoming it is just as important as developing new rockets or life support systems, because the vehicle that carries us must be able to survive the journey. The station's enduring presence is a daily victory in this battle, a symbol of our ability to build something that can, for a time, withstand the unforgiving reality of space. The same harsh space environment that slowly wears down the station's materials also wages a relentless war on the human body, and the effects of long-term exposure to microgravity are profound, insidious, and something every astronaut must contend with. While the station's structure faces external degradation, the crew inside experiences an internal transformation that challenges their very biology from the moment they arrive. The most obvious change is the loss of muscle mass and bone density. On Earth, our muscles and bones are constantly working against gravity, which maintains their strength. In space, that constant resistance vanishes, and the body, being highly efficient, starts to shed what it perceives as unnecessary mass. Astronauts can lose up to 1% of their bone density per month, particularly in weight-bearing bones like the hips and spine, a rate far exceeding that of osteoporosis on Earth. This decalcification leaves bones brittle and increases the risk of fractures, both during the mission and upon return to gravity. Similarly, muscles atrophy, especially in the legs and back, as they are no longer needed for standing or walking. To combat this, astronauts are required to exercise for approximately 2 hours every single day, using specialized equipment like the Advanced Resistive Exercise Device, which simulates weightlifting, and treadmills and stationary bicycles that they must be strapped onto. However, this rigorous regimen only mitigates the loss. It does not prevent it entirely, and astronauts still return to Earth significantly weaker than when they left. Another bizarre and concerning effect is the fluid shift that occurs in microgravity. On Earth, gravity pulls bodily fluids down towards the feet, but in space, fluids redistribute evenly throughout the body, accumulating in the upper torso and head. This causes astronauts to have a perpetually stuffy nose, a puffy face, and thin-looking legs, often described as chicken legs. More seriously, this fluid pressure in the head is believed to be a primary cause of vision problems experienced by many long-duration crew members. The pressure on the back of the eyeball can flatten it, and the optic nerve can swell, leading to a condition called spaceflight-associated neuroocular syndrome, which can cause long-term or even permanent changes to eyesight. This is a major concern for missions to Mars, where such vision impairment could jeopardize the crew's ability to perform critical tasks. The cardiovascular system also undergoes significant deconditioning. The heart, no longer needing to pump blood against gravity, becomes weaker and smaller, The body's system for regulating blood pressure becomes less effective, leading to orthostatic intolerance, where astronauts feel dizzy or faint when they stand up upon returning to Earth. Their bodies have essentially adapted to a new normal without gravity, and readapting to Earth's pull is a painful and difficult process that requires extensive rehabilitation. The immune system also appears to function less effectively in space, making astronauts more susceptible to illness, and wounds may heal more slowly. The constant exposure to higher levels of radiation than on Earth also poses a long-term cancer risk, a danger that is carefully monitored but impossible to eliminate entirely. Perhaps the most complex challenge, however, is the psychological one, living in a confined, isolated environment, far from family and friends, with a small group of people and a relentless, busy schedule, takes an immense mental toll. The view of Earth is breathtaking, but it can also emphasize the distance and isolation. Crews experience what is known as the third quarter phenomenon, where morale often dips in the middle of a long mission. They are in a highly structured environment with little privacy, constant noise from machinery, and the ever-present background risk of a catastrophic failure. To support mental health, Mission Control schedules regular video conferences with families, ensures a supply of favourite foods and entertainment, and provides psychological support. The international nature of the crew adds another layer, as cultural differences and language barriers must be navigated with patience and understanding. The success of a mission depends heavily on crew cohesion and the ability to work together as a team under extreme stress. After returning to Earth, the recovery process is long and demanding. Astronauts undergo weeks and sometimes months of physical therapy to rebuild their muscle strength, bone density, and cardiovascular fitness. The simple act of walking again can be a challenge, requiring relearning balance and coordination. The psychological readjustment to life on Earth, with its sensory overload and lack of a rigid mission structure, can also be difficult. The data collected from astronauts on the ISS is invaluable for understanding these physiological effects and developing better countermeasures for future missions. For a journey to Mars, which could take up to 3 years, these challenges are magnified. We cannot currently simulate artificial gravity on a spacecraft, so we must find ways to make the exercise regimens even more effective, perhaps through new technologies or pharmaceutical interventions. Shielding from radiation remains a massive unsolved problem, requiring new materials or strategies. And the psychological support for a crew that will be farther from Earth than any humans in history, with communication delays of up to 20 minutes, will need to be entirely different, focusing on extreme autonomy and crew resource management. The astronauts on the ISS are therefore pioneers in the truest sense, volunteering their bodies for science to help us understand the limits of human endurance in space. Their sacrifice and courage provide the essential data that will enable the next giant leap, proving that while our bodies are fragile and adapted for Earth, our spirit and ingenuity can find ways to survive and eventually thrive in the cosmos. The long-term physiological effects are not just a medical curiosity. They are the primary obstacle to human deep space exploration, and overcoming them is as important as developing the rockets that will carry us there. Every day an astronaut spends on the station adds to our knowledge, helping to design future spacecraft, refine exercise protocols, and prepare for the day when humans set foot on another planet, having learned how to keep themselves healthy on the long journey through the void. The human body is the most complex system on the space station, and keeping it functioning is the ultimate goal, because all the technology in the world is meaningless without the people to operate it. So, the next time you see an interview with an astronaut, remember the incredible physical and mental transformation they have undergone, all in the name of exploration and expanding humanity's horizons. Their experience is a testament to our resilience and a reminder that the final frontier is not just outside the window, but within ourselves. While the human body struggles to adapt to the environment of space, the station itself represents a monumental achievement in mechanical and systems integration, specifically in the engineering of universal interfaces that allow different spacecraft and modules from various countries to connect seamlessly. This was not a simple plug-and-play operation. It required an unprecedented level of international cooperation and technical standardization to ensure that a module built in Japan could flawlessly dock with a node built in the United States, and that a Russian Soyuz spacecraft could bring crew to a station powered by American solar arrays. The physical docking mechanisms themselves are marvels of precision engineering. Imagine trying to connect two school buses in mid-air, while both are moving at 17,000 miles per hour, and you have a basic idea of the challenge. The systems developed, like the common berthing mechanism used for module-to-module connections and the various docking adapters for spacecraft, had to be incredibly robust and forgiving of minor misalignments, yet precise enough to form a perfect, airtight seal. The initial contact is often made with a soft capture system, using guides and latches that allow for some flexibility, followed by a hard capture system that pulls the two halves together with immense force, engaging dozens of bolts to create a rigid connection. But the physical hookup is only the beginning. The real magic, and the greater challenge, lies in the interfaces behind the hatch. Once two elements are physically joined, they must become one integrated system. This means that electrical power must flow from one to the other without a hitch. The voltage, current, and frequency had to be standardized so that a Japanese laboratory module could draw power from the American solar arrays without frying its circuits. Data networks had to speak the same language, allowing commands and telemetry to pass freely between all segments of the station. The computers in a Russian module needed to understand and respond to requests from American control centers, and vice versa. This required the development of common communication protocols and data buses, a task that involved reconciling different engineering philosophies and legacy systems from various space programs. Then there are the fluid systems. Coolant loops needed to connect so that heat could be transferred from one module to another and ultimately to the radiators. The plumbing had to align perfectly, with connectors that would open only after a secure seal was confirmed, preventing any leaks of ammonia or water into the station's interior. Similarly, the air revitalization system depends on the free flow of atmosphere throughout the station. A docking port isn't just a door, it's a conduit for air, allowing the single, shared atmosphere to circulate and be processed by the life support systems, regardless of which module the crew is in. The development of these universal standards was a diplomatic achievement as much as a technical one. Engineers from NASA, Roscosmos, ESA, JAXA, DOT, and other agencies had to sit down for years of meetings, negotiating every detail. They had to overcome not just technical differences, but also language barriers, cultural approaches to problem solving, and even different units of measurement. The goal was to create interfaces that were not only functional, but also future-proof, capable of accommodating new vehicles and technologies that hadn't even been designed when the station's core standards were laid down. This foresight is why the station can today host commercial crew vehicles like SpaceX's Dragon and Boeing's Starliner, which use modernized docking systems that still adhere to the core principles of interoperability. The consequences of getting it wrong were unthinkable. A misaligned electrical connector could cause a short circuit, potentially leading to a fire. A faulty fluid coupling could result in a leak of toxic coolant or precious water. An imperfect seal on a passageway could lead to a slow leak of cabin air, a silent and deadly threat. Every docking was a high-stakes event, where the work of thousands of engineers and billions of dollars hinged on a series of latches and connectors engaging correctly. The astronauts training for these dockings spent countless hours in simulators, practicing every possible failure mode, because there was no room for error once the vehicles were in space. The success of this universal interface engineering is often overlooked, but it is the very reason the International Space Station exists as a single, cohesive habitat rather than a collection of separate, incompatible outposts. It allowed for a phased construction approach where new modules could arrive years apart and still integrate perfectly into the growing complex. This interoperability extends to the resupply vehicles. A Russian Progress spacecraft, a Japanese HTV, and an American Cygnus craft all use different primary systems on their own, but they all conform to the station's standards for docking or berthing, and for transferring cargo, fuel, and data. This redundancy is a key safety feature. If one country's launch system is grounded, others can pick up the slack, ensuring the station's crew never runs out of food, water, or spare parts. The knowledge gained from this endeavour is directly applicable to future projects like the Lunar Gateway, a planned space station orbiting the Moon that will involve many of the same international partners. The lessons learned about standardization and interface control will be critical for ensuring that modules from the United States, Canada, Japan, DOT, and Europe can work together seamlessly far from Earth. It also sets a precedent for the private sector, as companies developing their own space stations or orbital habitats will need to adopt similar standards to allow for visitation and resupply by a variety of vehicles. In essence, the universal interfaces are the unsung glue that holds the entire enterprise together. They represent a triumph of cooperation over competition, proving that nations with different languages, cultures, and political systems can agree on a common set of technical rules for the benefit of all. It's a quiet, behind-the-scenes kind of engineering that doesn't capture the public imagination like a rocket launch or a spacewalk, but it is every bit as vital. Without these carefully designed couplings and the years of painstaking international collaboration they required, the International Space Station would be nothing more than a collection of lonely, isolated tin cans drifting in the void, instead of the vibrant, interconnected microcosm of humanity that it is today. This success story provides a blueprint for how we will build the larger, more complex structures needed for long-duration missions to Mars and beyond, where interoperability between spacecraft from Earth and habitats constructed in situ will be absolutely essential for survival. The humble docking port, with its intricate arrangement of seals, connectors, and latches, is therefore a symbol of something much larger, our ability to overcome earthly divisions and work together to create something enduring in the harsh environment of space. It is a testament to the power of shared goals and meticulous engineering, ensuring that no matter who builds the next piece of the puzzle, it will fit perfectly with what came before, allowing the grand project of exploration to continue. The incredible engineering feat of making everything connect seamlessly was only possible because of an even more monumental achievement here on Earth: the coordination of funding and resources from multiple nations. A task so complex it rivals the technical challenges of building the station itself. The International Space Station is the most expensive single object ever constructed, with a total cost estimated at over $150 billion. This was not a check written by one country. It was a pieced together, decades-long financial commitment from the United States, Russia, Europe, Japan, and Canada, each with their own space agencies, political systems, and public opinions about spending such vast sums of money. Coordinating this international funding was a Herculean task of diplomacy and bureaucracy. The station's budget was not a single, static number agreed upon at the start. It was a constantly shifting landscape, vulnerable to economic downturns, changing political priorities, and annual budget negotiations in multiple countries' legislatures. A change in administration in the United States or a shift in political focus in Russia could threaten funding for a critical module or necessary technology, causing delays and forcing redesigns. The partners had to agree not just on who would pay for what, but also on the sequence of construction. Which module would go up first? Which partner would provide the critical life support or power generation early on? These were not just technical decisions. They were intensely political, involving national prestige and the allocation of billions of dollars. The very survival of the project depended on the continuous willingness of these nations, which in other contexts were competitors or even adversaries, to cooperate for a common goal. This required building trust and establishing intricate legal frameworks, like the Intergovernmental Agreement, which laid out the rules for ownership, utilization, and liability. The financial complexity extended to the industrial level. Contracts for building modules and components were spread across thousands of companies in all the partner nations, creating a vast international supply chain that had to be managed and kept on schedule. A delay or cost overrun at a factory in Italy could impact the launch schedule of a space shuttle from Florida, which in turn would delay a spacewalk by a Canadian astronaut using a Japanese robotic arm to install a European module. Keeping this entire ecosystem synchronized over more than a decade of assembly was a logistical nightmare. The funding model also influenced the station's design and capabilities. Decisions about what to build and when were often driven by budget availability rather than pure engineering optimality. For instance, the cancellation of a dedicated NASA centrifuge module, which would have been crucial for studying the effects of artificial gravity on animals, was a direct result of budget constraints. This meant that some scientific opportunities were lost forever due to financial, not technical, limitations. The constant need to justify the station's cost to politicians and the public also shaped its mission. A greater emphasis was placed on producing tangible scientific results and educational outreach to demonstrate the return on this massive investment. This financial pressure continues to this day, as the partners debate the station's future and the funding required to maintain it through the end of this decade. The end of the Space Shuttle program created another financial upheaval, forcing NASA to rely on and fund commercial partners like SpaceX and Boeing to develop new crew transportation systems, which itself was a new and risky financial model. The story of the ISS's funding is a testament to the fact that grand exploration projects are as much about economics and politics as they are about rocket science. It proves that even when the technical know-how exists, the sheer cost of space exploration necessitates international partnership. The station stands as a symbol of what can be achieved when nations pool their resources, but it also serves as a cautionary tale about the fragility of such alliances. The ongoing operations cost billions per year, and securing that funding is a perpetual battle as we look to future projects, like a lunar space station or missions to Mars. The lessons from the ISS funding model are clear. International collaboration is essential for sharing the immense financial burden, but it comes with the added challenges of political instability, bureaucratic inertia, and the difficult task of aligning the strategic interests of multiple independent nations. The success of the ISS in overcoming these earthly hurdles is perhaps its most profound legacy, demonstrating that humanity can not only engineer a way to live in space, but can also engineer the complex political and financial structures on Earth required to make it happen. It is a reminder that the next giant leap will require opening not just new frontiers in space, but new chapters in international cooperation and sustained financial commitment, challenges that may ultimately be more difficult than solving the physics of propulsion or radiation shielding. The station is, therefore, a dual monument to human engineering in the vacuum of space and to human negotiation in the conference rooms of Earth. All that intricate international funding and complex engineering would be meaningless without the highly trained individuals who bring the station to life. And the preparation they undergo is as rigorous and demanding as any aspect of the construction itself. Astronauts on the International Space Station are far more than just pilots. They are engineers, scientists, medical officers, and maintenance technicians all rolled into one, requiring a depth of knowledge that takes years to build. Their training is an intensive, multidisciplinary marathon designed to make them absolute experts on every system aboard the orbiting laboratory. They do not just learn how to live in space. They learn how to be the station's first and last line of defense, capable of diagnosing and fixing virtually any problem that could arise, often with no immediate help from Earth due to communication delays. This process begins years before launch, with astronauts immersing themselves in the intricate details of the station's modules, from the complex life support systems that recycle air and water to the electrical grids and computer networks that keep everything running. They must understand the plumbing, the wiring, and the software to a level that would qualify them as master technicians on the ground. This is not superficial knowledge. It is a deep, functional understanding that allows them to trace a problem from a warning light on a console back to a specific valve or circuit board, often using schematics and procedures they have memorized or can quickly access. The training involves countless hours in high-fidelity simulators on Earth, full-scale mock-ups of the station's modules where they can practice every procedure, from a routine system checkout to a catastrophic emergency. They simulate hundreds of failure scenarios, relentlessly drilling for events like a sudden fire, a rapid loss of cabin pressure, or a toxic ammonia leak from the external cooling system. In these simulations, the training team on the ground throws every possible problem at them, forcing them to work under extreme pressure as a team, making critical decisions with limited information and time. This builds not only technical competence, but also the crucial team dynamic and decision-making skills needed when a real emergency happens hundreds of miles above the Earth. A significant part of their training is dedicated to preparing for spacewalks, or extravehicular activities, which are among the most dangerous tasks an astronaut can perform, since you cannot perfectly simulate the weightlessness of space on Earth. The next best thing is neutral buoyancy, achieved by training in gigantic swimming pools like the Neutral Buoyancy Laboratory in Houston. In this massive pool, astronauts don their bulky spacesuits and work on full-scale models of the station's exterior, practicing the precise movements and tool handling required for repairs and installations. Every task, from swapping out a battery to installing a new scientific instrument, is rehearsed over and over again underwater until it becomes second nature. The suit itself is a challenge to work in. It is pressurized and stiff, making even simple actions like turning a bolt a physically demanding effort that can lead to fatigue quickly. This training is essential for building the muscle memory and procedural fluency needed to work efficiently and safely in the actual vacuum of space, where a mistake can have fatal consequences. Beyond the engineering and maintenance, astronauts must also become proficient scientists. The station is a world-class laboratory, and crew members are responsible for conducting a wide array of experiments in fields like biology, physics, astronomy, and materials science. They need to learn the specific protocols for each experiment, how to operate the specialized equipment, and how to troubleshoot when things do not go as planned. One day they might be growing protein crystals to help develop new medicines, and the next they might be observing the behavior of fluids in microgravity or studying the growth of plants. This scientific training ensures that they can maximize the research output of the mission, often serving as the hands and eyes for scientists on the ground. The training is also cultural and linguistic. With an international crew, astronauts must learn to work seamlessly with colleagues from different countries, often learning enough of another language, typically Russian, to communicate effectively during complex operations. This cross-cultural teamwork is vital for mission success, as it fosters a collaborative spirit and ensures clear communication during high-stress situations. The psychological preparation is equally important. Astronauts are screened and trained to handle the isolation, confinement, and prolonged separation from family and friends. They learn coping strategies and team-building exercises to maintain morale and cohesion during their 6-month or longer stays in space. This comprehensive, all-encompassing training regimen is what transforms a select group of individuals into a capable, resilient, and autonomous orbital crew. They are not passive passengers. They are active operators and problem solvers. When a carbon dioxide scrubber fails or a computer needs rebooting, they do not wait for a command from Houston. They assess the situation and execute the repair based on their extensive training. This level of autonomy is not a luxury. It is a necessity for survival, given that a real-time conversation with mission control is impossible during much of the orbit. The investment in this human capital is enormous, but it is absolutely essential. The station's systems are complex and interconnected, and the environment is unforgiving. Only through this profound and multidisciplinary preparation can astronauts hope to manage the myriad challenges of living and working in space. They are the ultimate generalists in a world of specialists, and their ability to adapt, improvise, and overcome is the human glue that holds the entire enterprise together. This training evolution never really stops, even while on orbit. Astronauts continue to train for upcoming tasks using virtual reality and simulators, and they spend hours in conference with experts on the ground. The knowledge and experience gained from each mission feed back into the training program for the next crew, creating a continuous cycle of improvement and learning. As we look to future missions to the Moon and Mars, where crews will be even more isolated and self-reliant, the lessons learned from the intensive training of ISS astronauts will be more critical than ever. It is a testament to human adaptability and the relentless pursuit of competence, ensuring that when we send people into the harshness of space, they are not just going along for the ride, they are fully prepared to be the masters of their spacecraft, capable of handling whatever the universe throws at them. This human element, the years of dedication and study, is what truly enables the station to function, turning a collection of metal modules into a vibrant, productive, and safe home in the cosmos. After all that intensive training prepares astronauts to handle emergencies and complex science, their daily routine is dominated by two relentless and mundane yet critically important tasks: dealing with the station's trash and ensuring the continuous flow of supplies from Earth. It is a constant cycle of consumption and replenishment that defines life aboard the orbiting laboratory, and the logistics involved are a masterpiece of planning and execution. The station generates a significant amount of waste every single day, from food packaging and used hygiene products to leftover materials from experiments and broken equipment. In the confined environment of the station, there is no outside to throw anything away. The concept of taking out the trash simply does not exist in the way we know it on Earth. This is not just a matter of cleanliness. It is a serious safety issue. If waste were simply jettisoned into space, it would immediately become dangerous space debris, adding to the millions of fragments already orbiting Earth at high speeds. Each piece of trash, no matter how small, would become a potential projectile capable of causing catastrophic damage to the station or other spacecraft upon impact. Therefore, every item must be meticulously managed and stored. Used food pouches, wipes, clothing, and other dry waste are compacted as much as possible and stored in designated bags and containers. Liquid waste from hygiene activities and experiment runoff is carefully processed through the water recovery system, but solid waste presents a unique challenge. It accumulates over time, taking up valuable space inside the modules and requiring a disciplined storage protocol. The solution to this accumulating problem lies in the same vehicles that bring supplies to the station: the uncrewed cargo spacecraft. Ships like the Northrop Grumman Cygnus, the Russian Progress, and previously the European ATV and Japanese HTV are not just delivery trucks. They also serve as garbage trucks for their return journey. Once these spacecraft have been unloaded of their precious cargo of food, water, scientific equipment, and spare parts, the crew carefully fills them with the accumulated bags of solid waste. This process requires careful packing to maximize space and ensure the load is secure for the spacecraft's departure. When the cargo ship is full, it is sealed and then remotely undocked from the station. Instead of returning to Earth, these spacecraft are commanded to perform a deorbit burn, guiding them on a trajectory that ensures they burn up completely and safely in the upper atmosphere over a remote area of the Pacific Ocean. This controlled disposal is a crucial part of the station's operational cycle, preventing the creation of new space junk and keeping the living environment habitable. However, this waste management system is entirely dependent on the timely arrival of these cargo vessels, which leads to the other half of the challenge: the incredibly complex and frequent resupply logistics. The International Space Station is utterly dependent on Earth for survival. It is not a self-sustaining colony. It is an outpost that requires a constant, reliable lifeline of resources. Everything the crew needs to live and work must be launched from Earth, and the list is extensive. This includes food and water for drinking and rehydrating meals, nitrogen and oxygen for the atmosphere, propellant for the station's thrusters to maintain altitude, spare parts for everything from computers to toilet components, and new scientific experiments to be conducted. The planning for this supply chain is a global effort, involving multiple space agencies and commercial partners, and it operates on a tight schedule. Resupply missions are launched every few months, and a delay of even a few weeks can have serious consequences. For instance, if a cargo launch is postponed due to weather or technical issues, the crew on board may have to begin rationing certain resources. Water is particularly critical. While the water recovery system recycles about 90% of it, the system itself requires resupply of filters and chemicals, and there is always some loss. A significant delay could force the crew to reduce water usage for hygiene or even drinking, impacting their health and morale. Food supplies are carefully calculated, but a prolonged delay could mean moving to emergency rations. Spare parts are another vulnerable area. The station is a complex machine with thousands of components that can and do fail. There is a limited inventory of spares on board, and if a critical system like a pump or a carbon dioxide scrubber fails and no replacement is available, it could force a partial evacuation or even endanger the entire mission. Therefore, the logistics team on the ground maintains a sophisticated inventory management system, predicting what will be needed months in advance and scheduling launches accordingly. The process of launching and docking a cargo ship is itself a high-stakes operation. The spacecraft must be built, loaded, and launched on a precise trajectory to rendezvous with the station, which is moving at 17,500 miles per hour. Once in close proximity, the station's robotic arm, operated by astronauts, often grapples the spacecraft and berths it to a docking port. The crew then begins the time-consuming process of unloading, which can take several weeks, while simultaneously repacking the vehicle with trash and other items for disposal. This entire operation requires flawless coordination between the crew in orbit and mission control centers around the world. The financial cost of this supply chain is astronomical, with each launch costing hundreds of millions of dollars. But it is the unavoidable price of maintaining a continuous human presence in space. The reliance on this Earth-based logistics train also highlights the fragility of our current approach to space exploration. For future missions to the Moon or Mars, where resupply from Earth would be infrequent or impossible for long periods, developing advanced recycling technologies and in situ resource utilization will be essential. But for the International Space Station, the weekly unpacking of fresh food and supplies is a welcome reminder of home and a tangible symbol of the immense effort required to keep the station alive. It is a silent, ongoing partnership between the planet and its orbital outpost, a dance of rockets and robotics that ensures the lights stay on and the air remains breathable for the intrepid individuals living on the frontier. The smooth operation of this system is a testament to human ingenuity and organizational skill, but it is a constant reminder that in space, there are no simple trips to the store. Every candy bar and every spare bolt represents a monumental achievement of engineering and logistics. This cycle of delivery and disposal is the unglamorous backbone of space station operations, the routine work that enables the extraordinary science and exploration that capture our imagination. So, while we marvel at the breathtaking views and groundbreaking research, let us not forget the less celebrated but equally vital efforts in waste management and resupply, the endless chore of taking out the cosmic trash and waiting for the next delivery from home, a chore that keeps humanity's foothold in space secure and sustainable. The astronauts, trained for every contingency, approach this daily task with the same professionalism they apply to a spacewalk, knowing that the habitability of their home and the success of their mission depend on it. This relentless logistics chain is the station's beating heart, and every successful cargo mission is another breath of life, ensuring that the incredible journey of the International Space Station continues, one carefully packed shipment at a time. The constant flow of supplies is a lifeline, but it is not an infinite one, and when something breaks on the station, the crew cannot simply call a specialised technician or order a next-day delivery for a replacement part. They become a self-contained repair shop, operating with a limited toolkit and a finite cache of spares, tasked with fixing highly complex systems under immense pressure, often with step-by-step guidance from experts on Earth who are seeing the problem through a camera lens and data streams. This reality of in-orbit maintenance transforms every astronaut into a master troubleshooter and improviser. The process begins when a warning alarm sounds or a system behaves unexpectedly. The crew's first step is diagnosis, which is a collaborative effort with mission control. They describe the symptoms, read off error codes from computer screens, and use handheld sensors to gather data, all while specialists on the ground analyze telemetry in real time. This remote consultation is crucial, but it is hampered by the communication delay and the fact that the ground team cannot see, hear, or feel what the crew is experiencing. The astronauts are the eyes and hands on the scene, and their detailed observations are the foundation for any repair plan, once the faulty component is identified. The next challenge is accessing it. The station's interior is a densely packed maze of equipment, wires, and fluid lines, and a critical valve or circuit board might be buried behind several layers of panels and other systems. The design philosophy had to prioritize serviceability, but space is so limited that even simple access can require the careful removal of dozens of bolts and the temporary disconnection of other components. A slow and meticulous process in microgravity where every removed part must be secured to prevent it from floating away. Then comes the repair itself, which is where ingenuity often takes over. The spare parts on board are limited to the most critical and most likely to fail items. If the exact replacement part is not available, the crew and the ground team must improvise. This has led to some remarkable feats of space MacGyvering. Astronauts have crafted makeshift tools from available materials, used binder clips as temporary clamps, and repurposed parts from one system to temporarily fix another. The advent of 3D printing on the station has been a game changer in this regard, allowing mission control to design a custom tool or adapter on Earth and then beam the digital file to the station, where the crew can print it out in plastic within hours. This ability to manufacture tools on demand significantly enhances their self-sufficiency. However, not all repairs are so straightforward. Some failures involve systems that are outside the station's hull, requiring a spacewalk to fix. These are the most complex and dangerous repairs, reserved for critical systems like the external cooling loops, robotic arms, or solar arrays. Preparing for an emergency spacewalk is a massive undertaking, involving hurried suit preparations, briefings, and the immense psychological pressure of knowing that a mistake during the repair could have catastrophic consequences. The time factor is always present. A failure in a critical system like the oxygen generator or a primary carbon dioxide scrubber cannot be left for long. The crew may have to work in shifts around the clock to get it back online. fueled by urgency and the knowledge that their survival depends on it. Even for less critical systems, downtime can mean lost scientific data or reduced operational capability, so repairs are almost always conducted under a time crunch. This environment fosters a unique problem-solving mindset. Astronauts are trained to remain calm and methodical, systematically eliminating potential causes and validating each step of the repair. They document their work with photos and videos, creating a knowledge base for future crews who might face a similar issue. The psychological strain is significant. They are not only performing a difficult technical task, but also carrying the weight of knowing that a failed repair could jeopardize a multi-billion-dollar asset and their own safe return. The ground support team is their backbone during these operations, with engineers and designers who originally built the systems often participating in the troubleshooting calls, offering insights from their years of experience. This partnership between orbit and Earth is a powerful thing, a blend of real-time hands-on experience and deep institutional knowledge. After the repair is complete, the work is not over. The crew must test the system thoroughly to ensure it is functioning correctly and safely. And then they must stow all their tools and replace all the panels, returning the station to its normal operational state. The used or broken part is then carefully logged and stored, eventually to be packed into a departing cargo vehicle for disposal. Every repair, whether a simple swap of a fan unit or a complex spacewalk to fix a robotic arm, adds to the collective experience of operating in space. The lessons learned from each failure and each successful fix are incorporated into the design of future spacecraft, making them more robust and easier to maintain. This continuous cycle of failure, diagnosis, repair, and learning is an integral part of life aboard the International Space Station. It is a testament to human resilience and adaptability, proving that even when faced with a broken piece of equipment millions of miles from the nearest hardware store, we can find a way to fix it. This capability is not just about keeping the lights on today. It is about developing the skills and confidence we will need for the much longer journeys to come, where crews will be so far from Earth that they will have to rely entirely on their own resources and ingenuity to survive. The space station is therefore the ultimate training ground for interstellar mechanics. A place where we are learning not just how to live in space, but how to fix our home when it breaks, ensuring that the journey of exploration can continue. While keeping the station's internal systems running through clever repairs and improvisation is a full-time job, there is an even larger and more constant battle being waged to keep the entire structure itself in the correct position and orbit. A delicate dance of physics and propulsion that happens automatically but requires meticulous planning. The International Space Station is not simply floating in a perfect, stable orbit. It is constantly fighting an invisible force that is trying to pull it back down to Earth. Even at an altitude of around 400 kilometers, there are still trace molecules of Earth's atmosphere, and as the station speeds along at 28,000 kilometers per hour, it collides with these particles. This creates a tiny but persistent force called atmospheric drag, which acts like a gentle but relentless brake, slowly sapping the station's energy and causing it to lose altitude. Without any intervention, this drag would eventually cause the station to spiral lower and lower until it re-entered the atmosphere and burned up. To counteract this, the station must be regularly reboosted, pushed into a higher orbit to compensate for the energy lost to drag. This is not a simple task. It involves carefully calculated burns from thrusters. The station itself does not have large, primary engines for this purpose. Instead, it relies on the thrusters of spacecraft that are docked to it, primarily the Russian Progress cargo vehicles, or the engines on the Russian Zvezda service module. The process is a precise orbital maneuver. Flight controllers on the ground calculate the exact amount of thrust needed and the duration of the burn to raise the station's orbit by a few kilometers. The crew is informed, and, at the appointed time, the thrusters fire, often for several minutes. gently pushing the entire massive complex to a safer altitude. These reboost maneuvers are not rare. They are performed every few months, and sometimes even more frequently if solar activity is high, as a more active sun can cause the upper atmosphere to expand, increasing drag. But maintaining the right altitude is only half of the story. The station's orientation, or its attitude, is equally critical and requires constant adjustment. Attitude control is about which way the station is pointing in space. This is not arbitrary. It is essential for the station's survival. The enormous solar arrays need to be angled towards the sun to generate maximum power. At the same time, the large radiators on the truss must be pointed towards the dark, cold void of space to efficiently dump the waste heat generated by all the station's systems. If the station were to lose attitude control and start tumbling, it could quickly lose power and overheat, leading to a catastrophic failure. Maintaining this precise orientation is the job of a system called Control Moment Gyroscopes, or CMGs. These are massive, spinning flywheels housed in the station's truss. By changing the speed and direction of these spinning wheels, the station can rotate itself without using any propellant, a brilliant application of conservation of angular momentum. The CMGS can exert torque, slowly and smoothly reorienting the entire station to keep the solar arrays sun-pointing and the radiators in the shade. However, the CMGS have their limits. They can only store so much rotational energy, and they can become saturated if too many external forces act on the station over time. When this happens, the station must use its thrusters to desaturate the gyroscopes, essentially resetting them by firing small jets to counteract the built-up momentum. These external forces that disturb the station's attitude are constant and come from many sources. Even though the station is in microgravity, it is not free from gravitational forces. Earth's gravity is not uniform. It has slight variations due to the planet's oblate shape, a phenomenon called gravity gradient torque, which gently tries to align the station in a specific orientation. Another significant disturbance comes from the crew themselves. When astronauts move around inside the station, especially during vigorous exercise on the treadmill or the resistive exercise device, their movements impart small forces on the structure. Imagine pushing off a wall to float across a room. That action applies a tiny torque to the entire station, while each movement is small. The cumulative effect of 6 people living and working inside can slowly change the station's attitude. Operations outside the station, like the movement of the large robotic arm, Canadarm2 DOT, also generate reactive forces that must be accounted for by the attitude control system. The constant opening and closing of vents and the firing of small thrusters for other adjustments add to the perturbations. All of these disturbances mean that the attitude control system is never at rest. It is always making tiny, automatic adjustments to keep the station stable and correctly oriented. This is a continuous, energy-consuming balancing act. The electrical power needed to run the CMGS is significant, and the propellant used for desaturation burns and larger maneuvers is a finite resource that must be regularly replenished by visiting cargo ships. The loss of a CMG is a serious event, as happened in the station's early years, requiring a reconfiguration of the control system and relying more on thruster firings, which consume precious fuel. The planning for all these maneuvers is a complex science. Flight dynamics officers on the ground use sophisticated software to model the station's orbit and attitude, predicting drag effects and planning reboost maneuvers years in advance. They must coordinate these maneuvers with other activities, ensuring that a reboost does not interfere with a spacewalk, a spacecraft docking, or a critical scientific experiment that requires a stable microgravity environment. The timing of these burns is precise, often occurring at the orbital location where the thrust will be most effective. The crew is largely spectators during these automated maneuvers, though they monitor the systems and are ready to take over in case of an anomaly. This relentless need for orbital and attitude control highlights a fundamental truth about living in low Earth orbit. Nothing is truly static. The station is not parked. It is perpetually falling around the Earth, and keeping it in its designated path requires constant, active management. It is a testament to the engineering that this process is so routine and reliable. But it is a routine built on a foundation of complex calculations and redundant systems. For future space stations around the Moon or Mars, the challenges will be different, with less atmospheric drag, but perhaps more significant gravitational perturbations from nearby planetary bodies. The lessons learned from managing the ISS's orbit and attitude are proving invaluable for these future endeavours. So, while the astronauts focus on their science and maintenance inside, an invisible, automated ballet of gyroscopes and thrusters is constantly at work outside, maintaining the delicate balance between falling towards Earth and flying freely in space, ensuring that the laboratory remains a stable platform for discovery and a safe home for its crew. This ongoing effort is a silent partnership between the station's hardware and the teams on the ground, a dance of physics that never stops, from the moment the station was assembled to the day it will ultimately be deorbited. It is the unspoken rhythm of life in orbit, the constant, gentle nudging that keeps humanity's foothold in space secure. The constant, automated dance of thrusters and gyroscopes that keeps the station stable is orchestrated by an unseen but utterly critical network of computers and software, the digital nervous system of the entire orbiting complex. This isn't like the latest laptop you can easily replace. The International Space Station relies on a vast and complex network of computers, many of which are based on technology from the 1990s and early 2000s. This might sound outdated, but there is a very good reason for it: sheer, proven reliability. In the unforgiving environment of space, you do not want to use the newest, untested hardware or software. You want systems that have been through years of rigorous testing and have a proven track record of not failing. These computers need to be incredibly robust, fault-tolerant, and capable of operating for years, even decades, without needing a simple reboot. A spontaneous reboot in the middle of controlling the life support system or during a critical maneuver could be catastrophic. The software that runs on these machines is equally hardened. It controls everything, from the subtle adjustments of the control moment gyroscopes that keep the station pointed correctly, to the precise mix of gases in the cabin air, to the management of electrical power across the solar arrays. This software is not a single, monolithic program period. It is a complex web of interconnected systems, each responsible for a specific function, but all needing to communicate and cooperate seamlessly. Think of it as the station's brainstem, handling all the automatic, vital functions that keep the crew alive and the station functioning, often without any human intervention. Updating this software is a nerve-wracking process that is undertaken with extreme caution. On Earth, you might not think twice about installing a software update on your phone, even if it occasionally has bugs. In space, a bug in a software update could have dire consequences. Before any new software is uploaded to the station, it undergoes months, sometimes years, of testing on identical ground-based systems. Engineers simulate every possible scenario to catch any errors. When it is finally time for the update, the process is meticulously planned. It often happens during a quiet period, with the crew fully briefed and ready to switch to backup systems or manual control if anything goes wrong. The update is transmitted from the ground and installed on the computers, a process that can take hours, during which certain systems might be operating in a reduced functionality mode. Everyone breathes a sigh of relief only after the new software is running perfectly and all systems are verified to be operating normally. Another immense challenge is the integration of new hardware and technologies with this legacy computer architecture. Over the station's lifetime, new modules with more modern computers have been added. and commercial cargo and crew vehicles from companies like SpaceX and Boeing dock with their own advanced systems. Getting these new systems to talk to the station's older core computers requires intricate translation layers and interface software. It is like trying to connect a brand new smartphone to a decades-old mainframe. They speak different digital languages. This often meant that adding a new module required not just physical connection, but also a delicate upgrade or replacement of the older computer systems to handle the new data loads and communication protocols. This is a surgical operation in a live environment. You cannot just turn the station off to swap out a computer. The crew must carefully install new hardware, often during a spacewalk if it is an external component. And then the ground team must gradually bring the new systems online while ensuring they do not disrupt the ongoing operations of the rest of the station. The consequences of a widespread software or computer failure are unthinkable. A single point of failure could cascade through the systems. A bug in the software controlling the thermal system could lead to overheating or freezing. A fault in the power management software could cause a brownout, disabling critical life support equipment. A glitch in the navigation software could impair the station's ability to avoid space debris or maintain its attitude, leading to a loss of power or even a collision. The design philosophy, therefore, is built around redundancy. Critical systems have multiple, independent computer systems running in parallel. If one computer fails, another can instantly take over without any interruption in service. This redundancy extends to the networks themselves, with multiple data paths to ensure that communication between systems is never lost. The crew is trained to handle computer failures, with procedures to isolate malfunctioning units and switch to backups. Despite all this redundancy and careful planning, the risk is always present. The software is so complex that it is impossible to test for every single conceivable condition, especially the unique and unpredictable environment of space. Radiation from the sun and cosmic rays can also cause single-event upsets, where a high-energy particle strikes a computer chip and causes a bit to flip, leading to a temporary software error or even a hardware latch-up that can disable a component. The computers are shielded as much as possible, and their software includes error checking and correction routines to detect and fix these radiation-induced errors. But it is a constant battle. The story of the station's computers is one of remarkable achievement, a testament to building systems that are not just powerful, but profoundly reliable. It is a world where stability trumps speed, and where every line of code has been scrutinized for its potential impact on human life. This legacy of robust computing is directly informing the design of future spacecraft for lunar and Martian missions, where the communication delay with Earth will be so long that the spacecraft's computers will need to be even more autonomous and self-healing. They will need to diagnose and fix problems on their own, without waiting for instructions from mission control. The International Space Station has been the ultimate testbed for this kind of reliable computing in space, proving that we can build digital brains tough enough to survive the journey and smart enough to keep their human cargo safe. So, while the astronauts sleep, work, and gaze at Earth, this silent, steadfast network of computers and code is always awake, always monitoring, and always in control, a digital guardian ensuring that the delicate balance of life in the void is never broken. This invisible framework of ones and zeros is as much a part of the station's structure as the aluminum beams and titanium bolts, and its flawless operation is the unsung hero of every successful day in orbit. The lessons learned here, in integrating old and new, in managing risk, and in building fault-tolerant systems, are creating a foundation of knowledge that will support all our future ambitions in space, from commercial space stations to interplanetary travel. It is a quiet revolution in reliability, happening in the background, one line of code at a time. Of all the potential emergencies that the station's robust computers are programmed to monitor for, Few are as terrifying or as rapidly catastrophic as the threat of fire. In the sealed, oxygen-rich environment of a spacecraft, a fire is not just a danger, it is a potential endgame. The very air that keeps the crew alive becomes a potent accelerant, and with no way to escape into the void outside, a small flame can quickly become an inferno that consumes the entire habitat. This is not like a house fire on Earth, where you can run outside and firefighters can arrive with water and chemicals. In space, there is nowhere to run, and the physics of combustion are fundamentally different. The station's atmosphere is maintained at a pressure and oxygen concentration carefully balanced for human health and equipment function. But this carefully controlled mix is inherently more supportive of combustion than the air we breathe at sea level. Every material brought on board, from plastic panels and fabric partitions to cable insulation and experiment components, is meticulously screened for flammability. Engineers have gone to great lengths to select materials that are fire resistant, but the risk can never be reduced to absolute zero. A short circuit in a wire, an overheated electrical component, or a malfunctioning experiment could provide the initial spark. Once a fire starts, the microgravity environment changes everything. On Earth, hot air rises, carrying flames upward and drawing in fresh oxygen from below, creating the familiar shape of a flickering fire. In microgravity, there is no up for the hot air to travel. Consequently, flames do not leap and dance. They form stationary, dim blue spheres around the source of the fuel, a much more efficient and insidious form of combustion that can smoulder and spread in any direction. Without the convective currents of gravity, the fire does not draw fresh air to itself in the same way, but it can still spread along surfaces and through ventilation ducts. Fed by the station's constant air circulation, the smoke from such a fire is another deadly factor. On Earth, smoke tends to rise, collecting near ceilings and giving people time to crawl to safety underneath. In microgravity, smoke does not rise. It forms a thick, toxic cloud that quickly fills a module entirely, obscuring vision, causing disorientation, and poisoning the air with carbon monoxide and other lethal gases. This smoke can spread rapidly through the station's ventilation system, threatening the entire crew even in modules far from the original fire. The crew trains exhaustively for this nightmare scenario. They practice locating a simulated fire quickly, often by following the station's network of smoke detectors, which are placed throughout the modules. Their first response is to don oxygen masks connected to the station's emergency air supply, protecting their lungs from smoke inhalation. Then, they go to work fighting the fire itself. They use special extinguishers designed specifically for space. Water-based extinguishers are ineffective and dangerous in microgravity because water would form floating globules that could short out electrical systems. Instead, the crew uses carbon dioxide extinguishers that release a jet of gas to smother the fire by displacing oxygen. Fighting the fire requires a different technique too. Astronauts must be careful to not simply push the floating fireball around the module with the force of the extinguisher blast. They have to maneuver carefully to apply the CO2 directly to the base of the flame. Communication and coordination are vital, as one crew member fights the fire while others prepare for the worst-case scenario, a full station evacuation. This would involve the crew retreating to their lifeboats, the docked Soyuz or Crew Dragon spacecraft, sealing the hatches behind them, and preparing for an emergency undocking if the fire cannot be contained. The psychological terror of such an event is hard to overstate. The memory of the fire aboard the Russian space station Mir in 1997 looms large in the training of every astronaut. On that occasion, an oxygen-generating candle malfunctioned, creating a jet of flame that blocked the crew's access to one of their Soyuz escape vehicles. The fire burned for several minutes, filling the module with thick, black smoke and forcing the crew to don respirators. They eventually extinguished it, But the incident was a stark and terrifying reminder of how quickly a routine situation can turn life-threatening in space. Beyond the immediate flames and smoke, a fire can cause collateral damage that cripples the station. It can melt critical wiring, damage pressure hulls, and destroy irreplaceable scientific experiments. The soot from a fire can coat sensitive equipment, like the internal surfaces of the life support system, contaminating them and requiring a massive and difficult cleanup operation. The station is equipped with fireproof containers for storing particularly flammable materials, and protocols for using heat-generating equipment are strict, but the threat is always present, a silent spectre that demands constant vigilance. Every new item that is launched to the station is evaluated for its fire risk, and the crew is trained to be perpetually aware of any unusual smell, which is often the first indication of an electrical fire, the scent of overheating insulation. This ever-present risk shapes the very culture of living in space. It fosters a mindset of meticulousness and caution, where stowing a piece of equipment properly or reporting a faint, unusual odour is not just about tidiness, it is a critical act of survival. The extensive training, the specialised firefighting tools, and the robust emergency protocols are all layers of defence against one of the most primitive and formidable enemies an explorer can face. As we plan for longer missions to the Moon and Mars, where evacuation is not an option, the strategies for preventing, detecting, and suppressing fires will become even more critical. The experience gained from decades of managing this risk on the International Space Station is therefore priceless, teaching us not only how to fight fire in space, but, more importantly, how to design habitats and procedures to ensure that a spark never gets the chance to become a catastrophe. The silent, watchful smoke detectors and the strategically placed fire extinguishers are more than just safety equipment. They are symbols of the hard-earned knowledge that in the confined, precious atmosphere of a spacecraft, fire is an adversary that must be respected above all others. The constant vigilance against technical failures like fire underscores a less visible but equally formidable challenge that has been present since the station's conception. The monumental task of coordinating the work of 15 different nations, each with its own unique engineering traditions, cultural work styles, and technical languages. While the hardware in orbit represents a masterpiece of physical integration, the true miracle is the human collaboration that made it possible, a decades-long effort in diplomacy and project management that unfolded in conference rooms and design centres across the globe. This was not merely a technical partnership, it was an unprecedented experiment in international relations, where thousands of engineers, managers, and astronauts from vastly different backgrounds had to learn to speak a common technical language and trust each other with the most delicate and dangerous of tasks. The cultural and technical differences were profound from the outset. The American and Russian segments, which form the core of the station, were developed from fundamentally different design philosophies. Russian engineering, born from a legacy of robust, long-duration space stations like Mir, often prioritized simplicity and proven reliability, sometimes using systems that Western engineers considered outdated. American engineering, meanwhile, frequently pushed the cutting edge of technology, incorporating newer, more complex systems that offered greater capabilities but sometimes with less long-term flight heritage. These were not right or wrong approaches, just different, and merging them required immense compromise and respect. For instance, the choice of metals, the threading on bolts, the voltage of electrical systems, and even the units of measurement, imperial versus metric, all had to be harmonized. This went far beyond a simple translation. It was about reconciling entire engineering cultures that had evolved independently for decades. Language was a perpetual hurdle. While English and Russian became the official working languages of the program, this did not eliminate the risk of misunderstanding. Technical terms sometimes did not have perfect equivalents, and nuances in procedure or safety protocols could be lost in translation. A casual phrase from an American engineer could be interpreted as a firm commitment by their Russian counterpart, and vice versa. This required everyone involved to practice extraordinary patience and clarity, often repeating and confirming instructions to ensure everyone was precisely on the same page. Miscommunication was not just an inconvenience. A misunderstanding about a torque specification or a fluid connector could lead to a leak or a structural failure in orbit. The management structure itself was a novel creation. There was no single, supreme boss. Instead, a complex hierarchy of multinational boards and panels was established, where every major decision required consensus. This could be a slow and painstaking process. A proposed change to a software update or a new procedure might need to wind its way through committees in Houston, Moscow, Tokyo, Montreal, and Paris, gaining approval at each step. What might have been a quick decision in a national program became a weeks-long diplomatic exercise. This was necessary to ensure every partner's concerns were addressed and their national standards and safety regulations were met. But it added a layer of bureaucratic complexity that had no parallel in any previous engineering project. The human element on orbit reflected this ground-based collaboration. Astronauts and cosmonauts trained together for years, learning each other's languages and customs. An American astronaut learns to operate the Russian Soyuz spacecraft as a commander, and a Russian cosmonaut becomes an expert on the American segment's life support systems. They train in each other's countries, eat each other's food, and learn each other's emergency procedures. This cross-training is essential for building the trust and camaraderie needed when they are alone together in space, where they must function as a single, cohesive crew without regard for nationality. On the ground, teams of controllers in Mission Control Center in Houston and the Mission Control Center in Korolev, Russia, work in tandem, often sharing shifts and responsibilities. They develop personal relationships and a shared sense of purpose that transcends political tensions on Earth. Despite this, challenges persist. Political disagreements between partner nations on Earth can create a tense backdrop for the work in space. Funding debates in one country's legislature can threaten projects that other partners are depending on. The ebb and flow of international relations required the space station program to develop a certain resilience, an ability to compartmentalize and focus on the shared goal of keeping the station safe and productive, even when diplomatic relations on the ground were strained. The sheer scale of the documentation is another testament to the coordination challenge. Every procedure, every schematic, every software manual had to be translated and validated by all partners. Configuration control, keeping track of every single component and its version, became a logistical nightmare of epic proportions. Ensuring that a spare part launched from Japan would fit a module built in Europe and be installed by an astronaut trained in the United States using procedures written by a team in Russia. The success of the International Space Station in overcoming these hurdles is a powerful testament to what humanity can achieve when it chooses to collaborate. It proved that we could build a complex, interconnected, and fragile machine, not in spite of our differences, but by embracing them, by learning from each other's strengths, and by developing a shared culture of safety and excellence. The station is more than a scientific laboratory. It is a diplomatic achievement of the highest order, a symbol of peace and cooperation that has endured for over 2 decades. The lessons learned about managing multinational teams, harmonizing technical standards, and building trust across cultural divides are as valuable as any scientific discovery made on board. These lessons are now being directly applied to the next great international space project, the Lunar Gateway, which involves many of the same partners. The trust and processes painstakingly built over the life of the ISS have created a foundation for even more ambitious deep space exploration. So, while we rightly celebrate the technological marvel of the station itself, we should also remember the human marvel that built and operates it. the thousands of people who learned to bridge divides, who mastered the art of compromise, and who proved that, in the face of a grand challenge, our common humanity is the most reliable system of all. This ongoing experiment in international living and working is the station's quietest but perhaps most enduring legacy, demonstrating that the final frontier is not just a physical space to be conquered, but a social one to be carefully and collaboratively built, one understanding at a time. The incredible international collaboration that built and sustained the station now faces its final, and in many ways most delicate, shared challenge: planning for its safe and responsible conclusion. The International Space Station, for all its resilience and ongoing upgrades, cannot remain in orbit forever. Its systems will eventually succumb to the cumulative stresses of the space environment, and its orbit will naturally decay. The current plan is for a controlled decommissioning and deorbit sometime in the early 2030s, a manoeuvre that is as complex and hazardous as any in the station's history. Simply abandoning it is not an option. Left to its own devices, the station would become a massive, uncontrolled piece of space junk, a drifting hazard the size of a football field that would eventually re-enter the atmosphere unpredictably, raining debris over a potentially populated area. This is an unacceptable risk. So the partner agencies are committed to ensuring its end is as meticulously managed as its beginning. The preferred method is a controlled re-entry, a carefully choreographed final dance that will guide the entire structure into a remote, uninhabited region of the Earth's surface, specifically a vast area of the South Pacific Ocean around Point Nemo, a spot so far from land it is known as the Spacecraft Cemetery. This process will not be a simple matter of firing a few thrusters. The station is immense, weighing nearly 450 tons, and it is not aerodynamically stable. The goal is to use a series of burns from multiple, powerful spacecraft, likely specially modified Progress cargo vehicles or other future vehicles, to gradually lower the station's perigee, the lowest point in its orbit. This will require precise calculations and a significant amount of propellant. The vehicles will need to fire their engines at just the right time and for the correct duration to ensure the station's trajectory intersects the atmosphere at the exact angle needed. Too steep an angle, and the station would break up too high, scattering debris over a wider area. Too shallow an angle, and it might skip off the upper atmosphere, requiring another burn and complicating the prediction of the final impact point. The ideal scenario is for the immense friction of atmospheric re-entry to generate so much heat that the majority of the station vaporizes. But given its size and robust construction, several hundred tons of fragments are expected to survive the fiery plunge. These will include dense components like the massive structural trusses, docking mechanisms, and armour plating from the modules. The deorbit manoeuvre is designed to ensure all these surviving pieces fall harmlessly into the open ocean. The planning for this final act is already underway, requiring international agreement on the timing, the funding, and the specific procedures. It is a massive responsibility. A miscalculation could have dire consequences. The teams will rely on decades of tracking data and sophisticated models of how such a large, complex object breaks apart during re-entry. The final crew will have long since departed, and the station will be operating autonomously for its last hours, with commands sent from the ground to initiate the sequence. It will be a somber moment for the global space community, the end of a legendary chapter in human exploration. Yet, even in its departure, the station's legacy will be immense. The scientific knowledge gained is incalculable, spanning biology, medicine, materials science, and our understanding of the universe. It has been a testbed for the technologies we need for long-duration missions to the Moon and Mars, from life support and radiation shielding to advanced robotics and closed-loop recycling systems. Perhaps its greatest legacy, however, is the proof of concept for sustained international partnership in space. For over 2 decades, It has shown that nations with different histories, political systems, and cultures can work together peacefully and productively on a grand scale. The engineering and operational lessons learned from building, maintaining, and now decommissioning the ISS are directly informing the design of the next generation of commercial and international space stations. These future outposts will benefit from the hard-won knowledge of what works and what does not in orbit. The safe deorbiting of the ISS will itself set a crucial precedent for responsible behaviour in space, demonstrating that we must clean up after ourselves even with the largest structures. It underscores the growing problem of space debris and the importance of designing end-of-life disposal into future spacecraft from the very beginning. So, while the visible passing of the station from our skies will mark the end of an era, its influence will endure for generations. It has taught us how to live and work in space, how to cooperate on a global scale, and how to manage the entire life cycle of a major space asset. Its final journey, a controlled fiery descent into the remote Pacific, will be a testament to the responsibility that comes with exploration. It is a fitting end for a vehicle that has given so much to humanity, not a slow decay into a hazardous relic, but a deliberate, dignified, and safe return, ensuring that its legacy is one of inspiration and caution, paving the way for all that is to come. The story of the International Space Station, from its first module to its last fragment, is a complete narrative of human ambition, ingenuity, and ultimately, responsibility. A powerful reminder that our reach into the cosmos must be matched by our care for the orbital environment and our own planet below.